For decades, we've looked up and wondered, how far does it all go? Every telescope, every deeper look into the dark, has been NASA's attempt to find that final horizon, the place where space itself might run out of stars, light, and time. But the closer we get to that edge, the stranger the universe becomes. What did NASA find out there, and what does it reveal about the limits of reality itself? Let's dive into what NASA discovered at the edge of the universe. Stay tuned. The edge of observation. The universe, in all its staggering immensity, is far more than our eyes can comprehend. Yet for centuries, humanity has been looking outward, pushing against the limits of what we can see, striving to uncover what lies at the very edge of existence. When astronomers talk about the edge of the universe, they aren't imagining a wall or a cosmic border. Instead, they are describing the observable universe, the portion of the cosmos we can study because light or other signals from that region have had time to reach us. Everything we see, from distant galaxies to the faint afterglow of the Big Bang, exists within this observable sphere. Beyond it, the universe may stretch infinitely, or it may curve and twist in ways we cannot yet comprehend. But for now, it remains hidden, tantalizingly out of reach. The observable universe is huge beyond comprehension. Imagine all the stars in the night sky multiplied by billions upon billions. The furthest regions we can see are more than 46 billion light years away. That is a number so vast, it defies intuition. Every photon that reaches our telescopes has traveled across time itself, carrying with it whispers from the infancy of the cosmos. Some of the light we see today began its journey long before Earth even existed, long before our sun ignited, and long before life took hold on our planet. In a sense, looking at the edge of the universe is like reading the universe's autobiography, chapter by chapter, written in light. Yet observing the edge of the universe comes with profound challenges. The first, and perhaps most limiting, is the speed of light. Light may be fast, about 299,792 kilometers per second. But even at that speed, it takes time to travel across the cosmos. When we observe a galaxy 10 billion light-years away, we are seeing it as it appeared 10 billion years ago. We are looking into the past, glimpsing an era when the universe was young, and matter and energy behaved in ways that can seem almost alien compared to our current cosmic neighborhood. Distance is another formidable obstacle. The universe is so vast that even the most powerful telescopes can only capture a fraction of its light. As light travels across space, it spreads out, weakening in intensity. Cosmic dust and gas can block or scatter the faint signals arriving from these extreme distances. Sometimes, the light from distant galaxies is so faint that it merges with the background noise of the universe itself, making it almost impossible to distinguish. It is as if we are trying to hear a whisper across a stormy ocean. Possible, but incredibly difficult. Time adds another layer of complexity. The universe is not static, it is expanding, and it is changing. Stars are born, galaxies collide, and black holes devour matter in ways that transform the cosmic landscape. When we observe distant objects, we are seeing them as they were eons ago, not as they are today. Entire civilizations of stars may have lived and died while their light was traveling toward us. The edge of observation is not just a boundary in space. It is a boundary in time, a portal into epochs we could never witness firsthand. So, how do we push past these limitations? How do we peer further and further into the abyss of space, seeking the universe's most hidden secrets? The answer lies in ingenuity and technology. On July 29, 1958, amidst the height of geopolitical tension and the shadow of the Cold War, a bold declaration was made that would forever alter humanity's relationship with the cosmos. The United States officially established the National Aeronautics and Space Administration, an institution whose mission would be nothing short of monumental: to explore the heavens, to understand our universe, and to push the boundaries of what humanity could achieve. But NASA's birth was not the result of mere curiosity. It was a direct response to global competition, scientific urgency, and a deep human drive to understand the unknown. The late 1950s were turbulent times. The Cold War between the United States and the Soviet Union had escalated into a contest for technological supremacy, ideological dominance, and national pride. In 1957, the Soviet Union stunned the world by successfully launching Sputnik 1, the first artificial satellite to orbit the Earth. The world watched in awe and with a measure of fear, as a small metallic sphere, barely the size of a beach ball, silently circled the globe. The United States, long confident in its scientific and technological leadership, found itself scrambling. The launch of Sputnik ignited a nationwide sense of urgency, dubbed the Sputnik Crisis, and prompted the American government to recognize that space was now a frontier of both exploration and strategic importance. The founding of NASA in 1958 was a direct answer to this crisis. It was born out of a recognition that the skies were no longer merely the domain of science fiction or distant stars. They were the new theater of human ingenuity and international competition. Congress and President Dwight D. Eisenhower understood that without a coordinated, centralized effort, the United States would fall behind in a field that would shape the future of technology, defense, and knowledge itself. NASA's mandate was clear: to conduct space research, develop aerospace technology, and most importantly, explore beyond the boundaries of Earth. From its earliest days, NASA faced a staggering array of challenges. It was not merely a question of ambition, it was a question of logistics, funding, and unprecedented technological development. The idea of sending humans and machines into space had long captured the imagination of writers and scientists alike. From Jules Verne's From the Earth to the Moon to Konstantin Tsiolkovsky's pioneering theories on rocketry, but turning imagination into reality required solving problems that had never been solved before. Rockets had to be designed to withstand the vacuum of space, electronic instruments had to survive extreme temperatures, and communication systems had to reliably transmit data across hundreds of thousands of miles. NASA was, in essence, tasked with creating an entirely new branch of science and engineering from scratch. One of the key early missions shaping humanity's cosmic curiosity was Project Vanguard, intended to launch small satellites into orbit. Although the program initially struggled with setbacks, it demonstrated the potential of coordinated satellite launches. Another, perhaps more famous program, Project Mercury, aimed to send the first Americans into space. This program was both a technological challenge and a psychological endeavor. It sought to prove that human beings could survive in the harsh, airless environment beyond Earth's atmosphere. The successful flights of astronauts such as Alan Shepard, who became the first American in space in 1961, were milestones not only for NASA but for all of humanity. They marked the beginning of a new era where the sky was no longer the limit. The universe was the next frontier. Beyond the immediate thrill of the space race, NASA's formation represented something far more profound: a commitment to systematic scientific exploration of the cosmos. Early projects were focused not only on human spaceflight, but also on gathering data about Earth, its atmosphere, and the near-Earth environment. Satellites like the Explorer series provided vital information on cosmic rays, magnetism, and solar activity. These early missions laid the foundation for our understanding of space as a dynamic, complex, and interconnected system. The data they collected would inform decades of research and serve as stepping stones to deeper, more ambitious explorations. An often overlooked aspect of NASA's early mission was its foresight in developing telescopes and satellites designed to look beyond our solar system. While the public was captivated by astronauts orbiting Earth, NASA scientists were quietly preparing for a far greater challenge: observing the universe itself. The groundwork for this cosmic exploration involved designing instruments capable of detecting light and radiation across multiple wavelengths, from visible light to infrared and X-rays. These early projects set the stage for the eventual development of observatories such as the Hubble Space Telescope and, much later, the James Webb Space Telescope. It was in these quiet, meticulous preparations, calibrating sensors, testing optics, and refining launch technology, that the true vision of NASA as a window to the universe began to take shape. NASA's approach in its formative years combined ambition with collaboration. Scientists, engineers, and mathematicians from across the United States were brought together to solve seemingly insurmountable problems. The agency fostered partnerships with universities, research institutions, and even private companies, creating a culture of innovation that allowed for rapid technological advancement. This collaborative spirit was crucial not only for the development of hardware and software, but also for building the knowledge base necessary to interpret the flood of new data that space exploration would provide. The early decades of NASA's work were marked by remarkable achievements, each one expanding humanity's reach into the cosmos. The Lunar Orbiter program mapped the Moon in unprecedented detail, paving the way for the Apollo missions. The Pioneer and Voyager missions ventured into the outer solar system, capturing images and measurements of planets, moons, and the mysterious Kuiper Belt, which stretches beyond Neptune and contains countless icy bodies and dwarf planets. Each success added layers of understanding, revealing that our solar system was just one small corner of an immense and intricate universe. NASA's vision was never limited to nearby space. The agency understood that to truly grasp our place in the cosmos, humans would need to observe the universe at its farthest reaches. This understanding led to the development of space-based telescopes and satellite observatories designed to peer into the depths of space, capturing light that had traveled for billions of years. These instruments allowed scientists to study distant galaxies, observe the afterglow of the Big Bang, and uncover cosmic phenomena previously hidden from view. The ambition was staggering: to trace the history of the universe from its earliest moments to the formation of galaxies, stars, and planets, and ultimately to the cosmic structures at the edge of existence. Over the decades, NASA and other space agencies have built incredible instruments designed specifically to capture the faintest traces of light, heat, and radiation from the farthest reaches of the cosmos. These telescopes act as our eyes at the edge of existence, allowing us to see what no human could ever see with the naked eye. The Hubble Space Telescope, launched in 1990, revolutionized astronomy. Positioned above Earth's atmosphere, Hubble has provided an unobstructed view of the universe in visible, ultraviolet, and near-infrared light. Its deep-field images, like the famous Hubble Deep Field, reveal thousands of galaxies in a tiny patch of sky, some so distant that their light has traveled for more than 13 billion years to reach us. Hubble has shown us galaxies forming when the universe was less than a billion years old, giving scientists a window into the earliest stages of cosmic evolution. The telescope's ability to observe distant galaxies, nebulae, star clusters, has reshaped our understanding of the cosmos, revealing structures and patterns that were previously unimaginable. Then came the James Webb Space Telescope, a marvel of modern engineering and the successor to Hubble in many ways. JWST observes primarily in infrared light, which allows it to see through cosmic dust and capture light that has been stretched or redshifted by the expansion of the universe. This capability is crucial because the most distant objects are moving away from us at incredible speeds, stretching their light into longer wavelengths. JWST can observe the faint glow of the first galaxies, formed shortly after the Big Bang, providing insights into the origins of stars, galaxies, and even the elements that make up our own solar system. With its enormous mirrors and advanced instruments, JWST is helping humanity push the edge of observation further than ever before. Other telescopes complement these efforts. The Chandra X-ray Observatory allows us to see the universe in X-rays, a form of light invisible to human eyes. This reveals high-energy events such as black holes consuming matter, supernova explosions, and the hot gas-filling galaxy clusters. These energetic phenomena are crucial for understanding how galaxies evolve and interact, and they provide a glimpse of the universe's more violent and dynamic side. By observing X-rays, Chandra reveals aspects of the cosmos that would otherwise remain hidden, painting a more complete picture of what lies at the edge. Meanwhile, missions like WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have focused on the cosmic microwave background, the afterglow of the Big Bang itself. These observatories map the faint radiation left over from the universe's earliest moments, just 380,000 years after the Big Bang. Studying the CMB allows scientists to measure the universe's age, composition, and rate of expansion with astonishing precision. These data act as a kind of cosmic blueprint, revealing the seeds of galaxies, clusters, and the large-scale structure that fills the cosmos today. Observing the CMB is like looking at the universe's baby photos, understanding how it started, and seeing the origins of everything we know. Each of these instruments provides a unique perspective, and together they form a network of observation that allows us to reach toward the universe's limits. Hubble shows us stunning visual images. JWST peers through cosmic dust into the earliest galaxies. Chandra reveals energetic processes invisible to optical telescopes, and WMAP and Planck map the universe's oldest light. By combining data from these instruments, scientists can create a more complete and nuanced understanding of the edge of the observable universe. Even with all these tools, the edge of observation remains tantalizingly elusive. Every discovery seems to raise more questions than it answers. Why do galaxies form in certain patterns? How did the first stars ignite in the primordial darkness? What mysterious forces drive the universe's expansion at accelerating speeds? At the edge of observation, science encounters its own limits, forcing us to confront the unknown. But this is precisely what makes it thrilling. The edge is not a boundary to stop at. It is a horizon that challenges us, daring us to explore further, to innovate, and to imagine the unimaginable. In a way, observing the edge of the universe is also an act of patience and persistence. Light from the farthest galaxies has traveled billions of years, and we are only just beginning to catch glimpses of it. Each image, each measurement is a treasure, a fragment of a story that began long before humans walked the Earth. As technology improves and new instruments launch into space, the horizon continues to expand, revealing more of the universe's secrets. It is a journey without a final destination, a pursuit that may never truly end, because the universe itself is infinite, or at least far larger than we can ever hope to measure. The edge of observation is more than a scientific concept. Every time we peer into the heavens, we are confronting the vastness of existence and our own small place within it. And yet, through persistence and a relentless desire to understand, we are able to illuminate the darkness, one photon at a time. Cosmic horizons and the edge of the universe. The cosmic horizon represents the ultimate limit of what we can observe, the point beyond which light has not had enough time to reach us since the beginning of the cosmos. It is a boundary that is not physical, but temporal and observational. Every point in the universe has its own cosmic horizon. Because the universe has a finite age, about 13.8 billion years, the light from regions farther than a certain distance simply hasn't reached us yet. Even though the universe may stretch infinitely beyond what we can see, we are confined within a sphere of observation dictated by the speed of light and the age of the cosmos. This is why astronomers often speak of the observable universe as distinct from the entire universe. What we can see is only a fraction of what exists. Beyond this sphere lies the truly unknown, a region that may harbor structures, galaxies, and phenomena forever beyond our reach. One of the most fascinating aspects of cosmic horizons is that they are not fixed. The universe is expanding, stretching space itself. Galaxies that are currently visible may eventually drift beyond our observational limits, carried away by the accelerating expansion of space. In a distant future, some of the galaxies we see today may vanish from view entirely, leaving only their light as a faint memory. In this sense, the universe is like a living painting, constantly evolving, where the edges of perception are in motion. What we see now is a fleeting glimpse, a snapshot of a universe in flux. The concept of horizons also forces us to rethink our place in the cosmos. When we look out at distant galaxies, we are not just looking across space, we are looking across time. Each photon that reaches us carries information about the universe as it was billions of years ago, allowing us to reconstruct events from the distant past. In a way, the edge of the observable universe is not a spatial boundary, but a temporal one. It is the ultimate time machine, giving us the ability to witness the universe's earliest chapters and understand how it evolved into the vast and complex cosmos we inhabit today. For centuries, our view of the heavens was limited to what we could see with the naked eye or with small ground-based telescopes. The stars and galaxies that filled the night sky were awe-inspiring, yet they were only the closest, brightest objects. The farthest reaches of the universe remained invisible, cloaked in darkness. The invention of more powerful telescopes slowly revealed distant galaxies, nebulae, and cosmic structures. But even the most advanced ground-based instruments are limited by Earth's atmosphere, which blurs and absorbs much of the light arriving from space. This is where NASA stepped in, transforming the way humanity observes the cosmos. Since its founding in 1958, NASA has been at the forefront of pushing observational boundaries, launching telescopes and space observatories designed to escape the limitations of Earth and capture the universe in ways never before possible. By placing telescopes in orbit above the atmosphere, NASA enabled astronomers to see the cosmos in multiple wavelengths, from visible light to infrared, X-rays, and beyond. This opened a new era of discovery, allowing scientists to explore regions of space that had previously been inaccessible. The Hubble Space Telescope, perhaps NASA's most famous observatory, revolutionized our understanding of the universe. From its perch above Earth, Hubble has captured images of galaxies billions of light-years away, each one a window into the distant past. Its observations have allowed scientists to map the large-scale structure of the universe, measure the expansion rate of space, and study the formation and evolution of galaxies. The telescope's ability to peer into the farthest reaches of space has pushed the edge of observation outward, revealing a universe far more complex and dynamic than anyone had imagined. Following Hubble, the James Webb Space Telescope has taken humanity's view even further. Unlike Hubble, which primarily observes visible and ultraviolet light, JWST focuses on infrared light. Infrared has a remarkable ability to penetrate dust and gas, revealing stars and galaxies hidden from view in visible light. This makes JWST particularly powerful for studying the early universe, where the first galaxies formed within a few hundred million years after the Big Bang. By capturing this ancient light, JWST allows astronomers to see the universe as it was at its dawn, providing unprecedented insight into cosmic history and pushing the cosmic horizon farther than ever before. NASA's innovations are not limited to optical and infrared observations. The Chandra X-ray Observatory, for instance, allows scientists to study high-energy phenomena invisible in other wavelengths. Black holes devouring matter, supernova explosions, and the hot gas-filling galaxy clusters are all revealed in stunning detail through X-rays. By observing the universe in this energetic light, Chandra provides a different perspective on the cosmos, uncovering aspects of its structure and behavior that would otherwise remain hidden. Each observation adds a piece to the puzzle, extending the boundaries of what we can understand about the universe's edge. Meanwhile, NASA's missions dedicated to the cosmic microwave background, CMB, such as WMAP and Planck, have offered a glimpse even closer to the universe's origin. The CMB is the faint afterglow of the Big Bang, radiation that has been traveling through space for nearly 14 billion years. By mapping tiny variations in this radiation, scientists can reconstruct the universe's earliest moments and understand the distribution of matter that eventually formed galaxies and clusters. These observations provide a kind of cosmic blueprint, allowing us to peer past the stars and into the primordial universe itself. NASA's role in pushing observational boundaries is not just about building telescopes. It is about expanding the very concept of what is observable. Each new instrument, each new observation stretches the cosmic horizon outward, revealing regions of space and time that were previously hidden. The more we observe, the more we realize how much remains unknown. Every discovery leads to new questions. Why do galaxies form in certain patterns? What causes the mysterious acceleration of the universe's expansion? Are there structures beyond the observable universe that we may never detect? The edge of observation is a frontier in every sense, a place of endless curiosity, challenge, and possibility. One of the most exciting aspects of this pursuit is that it is ongoing. NASA is continually developing new instruments, technologies, and missions designed to see farther, clearer, and in new ways. The upcoming Nancy Grace Roman Space Telescope promises to survey vast regions of the sky with unprecedented clarity, while concepts like the Large UV Optical Infrared Surveyor envision even larger and more powerful space observatories capable of mapping galaxies at the universe's extreme edges. Each new telescope is a step forward in our journey, enabling us to explore regions that were once beyond imagination. Observing the edge of the universe is also a story of collaboration. NASA works closely with international partners, including the European Space Agency, ESA, and the Canadian Space Agency, CSA, pooling resources and expertise to create instruments that no single country could build alone. These collaborations have produced some of the most remarkable observations in human history, from high-resolution images of distant galaxies to the detection of gravitational waves and other subtle cosmic signals. Together, these efforts expand our observational reach and deepen our understanding of the universe. Yet even as NASA pushes the boundaries, the universe continues to surprise. Observations at the edge often reveal anomalies and phenomena that challenge established theories. Galaxies appear to form earlier than expected, cosmic structures are aligned in unexpected ways, and some regions of space exhibit behaviors that defy conventional physics. These surprises remind us that the edge of observation is not just a technical challenge. It is a realm where our understanding of reality itself is tested. Every observation is a dialogue with the universe, and every discovery reshapes the questions we ask. We see galaxies forming, stars igniting, and the faint afterglow of the Big Bang itself. We measure the expansion of space, map the invisible scaffolding of dark matter, and study high-energy phenomena that shape cosmic history. And yet, beyond this edge lies an infinite expanse, waiting to be explored, understood, and imagined. NASA has taken us closer to this edge than ever before, and as technology advances, the horizon will continue to recede, revealing more of the universe's secrets with each passing year. The early universe revealed. The early universe refers to the period immediately following the Big Bang, when the universe was only a few million years old. During this time, the universe underwent rapid expansion and cooling, and the fundamental components of matter and energy began to take the forms we observe today. Understanding the early universe is essential because it provides the foundation for the formation of galaxies, stars, and planetary systems, as well as the distribution of matter and energy that shapes the universe on the largest scales. The first few million years of the universe's history were dominated by high-energy processes. Initially, the universe was extremely hot and dense, consisting of a plasma of subatomic particles, including protons, neutrons, electrons, and photons. In this state, photons could not travel freely because they were constantly scattering off the charged particles. This period, known as the photon-dominated era, prevented light from moving across space and made the universe opaque. It was not until the universe cooled sufficiently for electrons and protons to combine into neutral atoms, a process called recombination, that photons could travel freely. This moment occurred roughly 380,000 years after the Big Bang, and resulted in the release of the cosmic microwave background, CMB radiation, which remains one of the most critical sources of information about the early universe. The CMB is the residual thermal radiation from the Big Bang, and it provides a snapshot of the universe at the time when it became transparent. Observing and analyzing the CMB allows scientists to determine the age, composition, and structure of the universe with high precision. The tiny variations in temperature observed in the CMB correspond to regions of slightly different density, which eventually led to the formation of galaxies and large-scale cosmic structures. Studying the CMB also provides evidence for the Big Bang theory and the process of cosmic inflation, a rapid expansion of space in the first fractions of a second after the universe formed. NASA has played a leading role in mapping and studying the CMB. The COBE, Cosmic Background Explorer mission, launched in 1989, provided the first detailed measurements of the CMB's temperature variations. COBE confirmed that the CMB is remarkably uniform across the sky, but it also detected slight anisotropies, small fluctuations in temperature that indicate the earliest seeds of structure in the universe. These measurements were critical for confirming theoretical predictions and earned John Mather and George Smoot the 2006 Nobel Prize in Physics. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, was launched in 2001 to map the CMB with higher resolution. WMAP produced detailed all-sky maps that allowed scientists to refine estimates of the universe's age to approximately 13.8 billion years and to determine its composition. According to WMAP's data, about 5% of the universe consists of ordinary matter, 27% is dark matter, and 68% is dark energy. WMAP's observations also confirmed that the universe is flat on large scales, consistent with predictions from cosmic inflation models. The mission provided critical data on the expansion rate of the universe, the density of matter, and the scale of initial fluctuations that led to the formation of galaxies. Building on WMAP's success, the Planck mission, launched in 2009, provided the most precise measurements of the CMB to date. Planck's instruments were capable of detecting temperature differences as small as a few millionths of a degree, revealing detailed structures in the early universe. The mission confirmed WMAP's findings regarding the universe's age, composition, and geometry, but also provided additional insights into the polarization of the CMB. Polarization measurements are important because they reveal information about the motion of matter and the influence of gravitational waves in the early universe. Planck's data allowed cosmologists to test models of the universe with unprecedented accuracy, improving estimates of fundamental parameters, such as the Hubble constant and the density of different forms of matter. The CMB has been critical for understanding the formation of cosmic structures. The tiny fluctuations in the early universe eventually amplified under the influence of gravity, leading to the development of stars, galaxies, and galaxy clusters. Observations of the CMB provide evidence for the distribution of matter in the early universe and allow scientists to study how structures evolved over billions of years. These observations have also led to insights into dark matter, which does not emit light but exerts gravitational influence, playing a key role in shaping the universe's large-scale structure. WMAP and Planck data also contribute to understanding cosmic inflation. Inflation theory proposes that the universe underwent exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion smoothed out irregularities and explains the uniformity observed in the CMB. By studying the anisotropies in the CMB, scientists can test predictions of inflationary models, such as the distribution and amplitude of fluctuations. The precision of WMAP and Planck has allowed cosmologists to narrow down the range of possible inflationary scenarios, making these missions essential for understanding the universe's earliest moments. NASA's work on the early universe extends beyond CMB observations. Instruments like the Hubble Space Telescope and now the James Webb Space Telescope, JWST, complement CMB data by observing distant galaxies whose light has traveled for billions of years. These observations allow scientists to compare theoretical predictions about early galaxy formation with actual data. The combination of CMB mapping and deep space imaging enables a comprehensive understanding of the universe's history, from the first seconds to the present. The early universe is also studied in multiple wavelengths, not just microwaves. Observations in infrared, X-ray, and other spectra help scientists detect the formation of the first stars and galaxies, the effects of reionization, and the behavior of primordial matter. By integrating data from different instruments and missions, researchers can reconstruct a timeline of cosmic events, from recombination and CMB release to the assembly of the first galaxies. NASA's multi-wavelength approach ensures a more complete understanding of the early universe and its subsequent evolution. NASA's data from WMAP and Planck have helped refine estimates of fundamental cosmological parameters. For instance, the Hubble constant, which measures the universe's expansion rate, can be estimated using CMB observations. While some discrepancies remain between CMB-based measurements and those obtained through local observations of supernovae and galaxies, NASA's contributions provide a crucial reference point for resolving these differences. By combining data from the early universe with more recent observations, scientists aim to achieve a unified understanding of cosmic expansion and the role of dark energy. The early universe also provides insight into the nature of fundamental particles and forces. During the first million years, conditions were extreme, and processes such as nucleosynthesis, the formation of the first atomic nuclei, occurred. Studying these processes allows scientists to test predictions of particle physics and to understand the abundance of elements like hydrogen, helium, and lithium in the universe. Observations of the early universe, therefore, bridge cosmology and fundamental physics, offering empirical data for theories that describe matter and energy under extreme conditions. NASA's insights into the Big Bang and inflationary theory. When scientists talk about the Big Bang, they aren't describing an explosion in space, they're describing an expansion of space itself. Everything from atoms to galaxies once existed in a single dense point that suddenly began to stretch outward. What NASA has done over the last few decades is gather the data that turned this concept from theory into measurable reality. The Big Bang theory explains how the universe expanded from an initial state of extreme heat and density around 13.8 billion years ago. But while the idea itself dates back to the early 20th century, it was NASA's space missions that provided the most concrete evidence for it. The discovery of the cosmic microwave background, the faint afterglow of that primordial event, gave scientists their first direct glimpse of the universe when it was less than 400,000 years old. Through missions like COBE, WMAP, and Planck, NASA didn't just observe this ancient light, it decoded it, pixel by pixel, to reveal how the universe took shape. The CMB isn't just a relic, it's a map, a frozen image of the universe at the moment matter and radiation parted ways. The slight irregularities NASA detected in that background light show where matter was denser in some spots than others. Over billions of years, gravity pulled those dense regions together, forming stars, galaxies, and clusters. What looks like random static is actually the blueprint of cosmic structure. But there's another layer to this story, the inflationary theory. In the early 1980s, physicists proposed that just a fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This idea was meant to solve a few problems, like why the universe looks so uniform everywhere we look, and why space appears flat instead of curved. For decades, inflation was only a mathematical solution. NASA's observations turned it into something tangible. Data from WMAP and Planck showed that the tiny temperature fluctuations in the CMB perfectly matched the predictions of inflationary models. If inflation hadn't happened, those fluctuations would look random or uneven. Instead, they follow a precise statistical pattern, one that suggests the universe expanded smoothly, stretching quantum ripples into the seeds of galaxies. This is one of the strongest indirect proofs of cosmic inflation we have. Another insight came from the geometry of the universe itself. The CMB revealed that space is flat, not curved inward like a sphere or outward like a saddle. This flatness implies that the universe's total energy density is very close to a critical balance point. Inflation neatly explains this. The rapid expansion would have smoothed out any initial curvature, much like how blowing up a balloon makes a small patch of its surface look flat. Without inflation, it would be almost impossible for the universe to be as balanced as it is today. NASA's CMB data also helped settle one of the oldest questions in cosmology. How old is the universe? Before space-based measurements, estimates of the universe's age varied widely. But by analyzing how light from the CMB stretched and cooled over time, NASA missions refined the age to about 13.8 billion years, give or take a few tens of millions. This figure has since become the standard in cosmology. The temperature map of the CMB also revealed the composition of the universe. Only about 5% of everything we see, the stars, planets, and galaxies, is made of ordinary matter. Around 27% is dark matter, an invisible substance that shapes galaxies through gravity, and roughly 68% is dark energy, a mysterious force driving the universe's accelerating expansion. These numbers emerged from NASA's data analysis of the CMB's fine details, the tiny variations in temperature and polarization that encode information about density and composition. The implications are huge. The Big Bang wasn't just the beginning of matter, it was the beginning of structure. The initial energy fluctuations recorded in the CMB became the skeleton of the cosmos. Without them, the universe would have remained an even fog of gas and radiation. NASA's data confirmed that cosmic structure isn't random. It follows patterns that trace directly back to the earliest measurable moment. NASA's findings also connected cosmology with fundamental physics. Inflation suggests that the laws of quantum mechanics, which govern subatomic particles, played a role in shaping the entire universe. The small fluctuations NASA measured in the CMB likely originated from quantum variations magnified to cosmic scales during inflation. This link between the smallest and largest scales of existence remains one of the most profound discoveries in science. Another key result from NASA's missions involves polarization in the CMB. As light from the early universe traveled through space, it became slightly polarized, meaning the orientation of its waves was subtly organized by cosmic forces. By studying this polarization, scientists can trace gravitational effects from the early universe and potentially detect signals from primordial gravitational waves, which inflation theory predicts. Planck's precise polarization maps brought us closer to confirming these predictions, even though the signals are faint and buried in cosmic noise. Beyond inflation, NASA's work helped identify one of cosmology's biggest mysteries: the universe's accelerating expansion. If gravity were the only force at play, expansion should have slowed over time. Instead, NASA's observations showed the opposite. The universe is expanding faster today than in the past. This discovery, combined with supernova data, pointed to the existence of dark energy. It also tied back to inflation. The same mechanism that caused rapid expansion at the universe's birth might echo today in a slower, persistent form. These insights changed how scientists think about the universe's fate. If dark energy continues to dominate, expansion will go on indefinitely. Galaxies will drift farther apart until they disappear from one another's view. NASA's data suggests this scenario, sometimes called the Big Freeze, is the most likely outcome. Inflation started the expansion, and dark energy seems destined to finish it. One of the most striking things about NASA's results is how consistent they are across different missions. COBE first detected the faint anisotropies in the CMB. WMAP mapped them in detail, and Planck refined them with unmatched precision, each mission built on the last, reducing uncertainty and confirming that the Big Bang and inflation are not just theoretical frameworks, but the most accurate models of reality we have. Even the smallest discrepancies NASA found became opportunities for deeper understanding. For instance, differences between the expansion rate measured from the early universe, CMB data, and that measured in the nearby universe using supernovae and galaxies have led to what scientists call the Hubble tension. This conflict could hint that our current physics isn't complete, that perhaps new forms of energy or subtle deviations from general relativity exist. In this way, NASA's discoveries haven't closed the book on cosmology. They've opened new chapters. NASA's exploration of the Big Bang and inflation reveals a consistent story. The universe is ancient, vast, and finely balanced. It began from an unimaginably hot and dense state, expanded faster than light for a brief instant, and gradually cooled into the cosmic web we see today. Every measurement, from the CMB's temperature to its polarization, strengthens the foundation of that story. But more than that, NASA has shown that the universe is not static. It evolves. It has an origin, a history, and a future. The agency's missions have transformed the idea of the Big Bang from a bold hypothesis into a precise scientific narrative supported by data that reaches back almost to the beginning of time itself. The hidden universe, the search for dark matter. There's something missing in our universe, something invisible, something that doesn't shine, doesn't reflect, and doesn't emit a single particle of light. Yet it's everywhere, surrounding galaxies, shaping the cosmos, and quietly deciding how everything moves. Scientists call it dark matter, and NASA's been on a decades-long mission to uncover its secrets. When astronomers first looked at the motion of galaxies, the math didn't make sense. The stars were moving too fast, spinning around their galactic centers as if there was far more gravity holding them together than what could be explained by the matter we could see. If visible matter, stars, gas, dust, were all that existed, galaxies should have torn themselves apart billions of years ago. But they didn't. Something unseen was keeping them intact. That was the first clue. The discovery came quietly in the 1930s when Swiss astronomer Fritz Zwicky studied galaxies in a cluster and noticed their speeds didn't match their visible mass. He proposed that missing mass, what he called dunkle materie, or dark matter, was providing the extra gravity. At the time, it sounded absurd. How could something we can't see make up most of the universe? But in the 1970s, American astronomer Vera Rubin made a discovery that changed everything. She studied how stars orbit inside spiral galaxies, including our own Milky Way. According to physics, stars near the edges should orbit slower than those near the center, just like planets do around the sun. But they didn't. Stars far from the center were moving just as fast, too fast. The only explanation was that an invisible halo of mass surrounded each galaxy, anchoring everything in place. Rubin's work was undeniable proof that most of a galaxy's mass is invisible, and that's when the hunt for dark matter truly began. Dark matter doesn't interact with light. That's why telescopes can't see it. It doesn't absorb, reflect, or emit electromagnetic radiation. We only know it's there because of its gravitational effects. Every time light bends around a massive object, a process called gravitational lensing, dark matter leaves its fingerprint. When NASA's Hubble Space Telescope looks deep into a galaxy cluster, the gravity from all that hidden matter bends space itself, distorting the light from galaxies behind it like a cosmic magnifying glass. By studying how that light bends, NASA can map the invisible. These gravitational lenses let scientists trace where dark matter hides, even though they can't see it directly. And what they've found is astonishing. In galaxy clusters like Able's 1689, Hubble's observations show that visible matter, all the stars, gas, and dust, makes up only a tiny fraction of the cluster's total mass. The rest is dark matter, stretching across space like a massive, unseen web. That web isn't random. It forms the cosmic skeleton of the universe, an invisible structure that everything else hangs upon. Galaxies, stars, and planets exist where dark matter clumps together most densely. Without it, there would be no galaxies, no stars, and no us. To understand how much of this invisible stuff exists, NASA turned to both observation and simulation. When satellites like WMAP and Planck mapped the cosmic microwave background, the leftover radiation from the Big Bang, they revealed tiny ripples in temperature across the sky. Those ripples show where matter was slightly denser in the early universe. The pattern of those ripples matches what would happen if dark matter were already present, shaping the flow of ordinary matter under gravity. Without it, the early universe's structure would look completely different. The data told a clear story. Dark matter makes up roughly 27% of the universe, while everything we can see, stars, galaxies, planets, even all living things, adds up to just 5%. The rest is a mysterious force called dark energy, which drives the universe's expansion. In other words, almost everything we know and touch is only a sliver of reality. NASA's telescopes have given scientists more than evidence. They've given them maps. The Hubble Space Telescope, launched in 1990, has been one of the most powerful tools for studying dark matter. Using deep space imaging, scientists have used Hubble's sharp vision to chart how dark matter is distributed across the universe. When light from distant galaxies passes through massive clusters, the warping patterns reveal where dark matter lies. This technique, called weak gravitational lensing, is subtle but incredibly powerful. It doesn't just show where matter is, it shows how it's moving. Over the years, Hubble has mapped the dark matter halos around galaxies, the bridges connecting clusters, and even the vast voids where matter is almost absent. One of Hubble's most striking achievements came from the study of a distant cluster known as the Bullet Cluster. This system is actually two galaxy clusters that collided hundreds of millions of years ago. When NASA analyzed the X-ray and optical data, scientists found something extraordinary. The visible gas had been separated by the collision, but the gravitational mass, the dark matter, had passed straight through, barely interacting at all. This was one of the most direct pieces of evidence that dark matter truly exists as a separate, invisible component of the universe. It doesn't behave like normal matter. It doesn't clump or heat up. It simply passes through, pulled only by gravity. As technology advanced, NASA's James Webb Space Telescope stepped into the story. Webb can see deeper into space and further back in time than any telescope before it. By studying the light from some of the earliest galaxies, it allows scientists to test how dark matter influenced their formation. In the early universe, dark matter acted as a gravitational scaffold. Ordinary matter, the kind that forms stars and planets, gathered where dark matter had already created invisible wells of gravity. JWST's infrared vision is now confirming that galaxies began forming sooner than anyone expected, suggesting dark matter's influence was even stronger and more efficient than previous models predicted. By comparing JWST's deep field images with dark matter simulations, scientists can refine our understanding of how structure emerged. It's as if NASA is building a time-lapse of the universe's growth, one data point at a time. But even with all this progress, one question remains: what is dark matter actually made of? NASA's observations have ruled out many possibilities. It's not ordinary matter hiding in faint stars or cold gas clouds. There simply isn't enough of that to account for the gravity we see. It's not black holes either, at least not in the amounts required. The leading ideas point toward exotic particles, things that don't fit into the standard model of physics. These hypothetical particles, like WIMPs, weakly interacting massive particles, or axions, would barely interact with normal matter. Billions might be passing through you right now, completely unnoticed. If they exist, they would explain everything: why galaxies hold together, why the cosmic web looks the way it does, and how the early universe formed structures so quickly. NASA doesn't detect these particles directly, but its observations guide where and how to look. By studying cosmic collisions, galaxy rotation, and gravitational lensing patterns, NASA helps narrow down the traits dark matter must have. Every new observation trims the list of possibilities. What's fascinating is how dark matter ties the entire universe together, literally and scientifically. It connects small-scale physics with the vastness of cosmology. It affects the rotation of galaxies, the shape of clusters, and even the expansion rate of the universe. Without dark matter, none of our models make sense. Gravity alone can't explain how galaxies formed so early after the Big Bang, or how the universe's large-scale structure evolved. It's the missing piece that makes the cosmic puzzle fit. And yet, despite decades of research, we've never seen it directly. That's what makes it so powerful and so frustrating. NASA's telescopes have shown us its shadow, its influence, its gravitational footprints, but not its face. Every map, every distortion, every rotation curve is a whisper of something enormous hiding behind the curtain of reality. Still, the evidence keeps piling up. Every time Hubble peers deeper into space, every time JWST captures light from the first galaxies, the patterns repeat. The same invisible hand shapes everything. So, what's next? NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in the next few years, will take this exploration even further. Roman will conduct large-scale surveys of the sky with unprecedented detail, mapping dark matter across billions of light-years. Its wide-field imaging will allow scientists to track how dark matter and dark energy interact, two forces that define the past and future of the universe. By comparing how galaxies cluster over time, Roman will help test whether dark matter behaves the same way everywhere or changes in different eras of the cosmos. It might even hint at new physics beyond anything we currently know. Dark matter is often called the universe's greatest mystery, but maybe it's more accurate to say it's the universe's greatest clue. It's the reason galaxies spin instead of flying apart. It's the unseen glue holding the cosmic web together. And thanks to NASA's work, from Hubble's lensing maps to JWST's deep fields, we're finally beginning to outline the invisible universe. Even though we can't see it, we can feel its pull. Every orbit, every cluster, every glimmer of light is shaped by something that refuses to reveal itself. And maybe that's the most humbling part, that the universe we think we know is just the bright tip of an unfathomable iceberg. And NASA's telescopes are finally helping us glimpse what lies beneath the surface of everything. Dark energy and the accelerating universe. For most of human history, the universe seemed like a fixed, eternal place, a grand stage that never changed. Stars appeared still. The sky seemed endless, but unmoving. Even scientists once believed that the cosmos was static, that it simply was. But when NASA's data began revealing the truth, the illusion shattered. The universe isn't still. It's not even slowing down. It's running faster and faster into the unknown. Something out there, something invisible, is pushing it apart. That something is dark energy. No one can see it. No one can touch it. Yet it's everywhere, woven through every corner of space. And according to NASA's most precise measurements, it makes up nearly 70% of everything that exists. Think about that. Almost 3/4 of the universe is made of something we don't understand. But the story of dark energy didn't begin with NASA. It began with a shock. In the late 1990s, two teams of astronomers set out to measure how fast the universe was expanding. They studied distant exploding stars called Type Ia supernovae, brilliant cosmic beacons that act as standard candles. By comparing how bright they looked versus how bright they should be, astronomers could tell how far away they were. The goal was simple: measure how much the universe's expansion was slowing due to gravity. After all, if everything began with the Big Bang, gravity should be pulling it all back together, right? But when the data came in, it told a completely different story. The universe wasn't slowing down, it was speeding up. This discovery, announced in 1998, stunned the scientific community. It overturned decades of assumptions and forced everyone, from physicists to philosophers, to rethink what they thought they knew about reality. Something was working against gravity, pushing galaxies apart faster and faster as time passed. That mysterious force was named dark energy. After the shock, NASA stepped up. The agency's space telescopes, Hubble, WMAP, Chandra, and later JWST, were all directed toward the same cosmic question: what is this invisible energy driving the expansion of the universe? Hubble played a central role early on. By observing hundreds of distant supernovae, it confirmed that the expansion rate of the universe wasn't just increasing. It was doing so unevenly, with slight variations depending on cosmic distance. This led to one of the biggest debates in modern astronomy. How fast is the universe actually expanding? That question is measured by something called the Hubble constant. But different instruments were giving different answers. NASA's Hubble data suggested one number, while satellites like WMAP and Planck, which looked at the early universe, suggested another. The disagreement wasn't small. It was enough to shake the foundations of cosmology. If these measurements are both correct, it means something fundamental about the universe is missing from our understanding. And that missing piece might be hidden in the very nature of dark energy itself. So what exactly is dark energy? Scientists have proposed several theories. Some believe it's a property of space itself, a built-in energy of the vacuum. Imagine space not as empty, but as a restless fabric filled with quantum fluctuations, constantly creating and destroying particles. This energy could act as a kind of cosmic pressure, pushing everything apart. Others suggest dark energy might change over time, not constant, but evolving. A mysterious field that grows stronger or weaker depending on the age of the universe. And then there's the most radical idea. Maybe our understanding of gravity is incomplete. Perhaps Einstein's equations don't fully apply on cosmic scales, and what we call dark energy is really a sign that gravity behaves differently than we think. NASA's telescopes are the detectives in this mystery. They can't see dark energy directly, but they can observe what it does. NASA's WMAP and Planck satellites gave scientists a way to look back almost 13.8 billion years to the very first light of the universe, the cosmic microwave background. That ancient glow still carries imprints of the universe's early density, temperature, and structure. By studying the tiny variations in that glow, NASA scientists could estimate how much matter, and dark energy existed throughout time. And what they found was astonishing. Billions of years ago, dark energy was almost non-existent. But as galaxies drifted apart, space itself expanded, and with more space came more dark energy. It was as if the more the universe stretched, the more this mysterious energy appeared, amplifying its own effect. It's a feedback loop written into the fabric of existence. And that's when a new question emerged. How far will it go? If dark energy continues to accelerate the universe's expansion, what happens next? NASA's data gives us several possibilities, and none of them are small. One scenario is called the Big Freeze. In this version, the universe keeps expanding forever. Galaxies move farther apart until their light can no longer reach each other. Stars burn out. New stars stop forming. Eventually, everything cools down to absolute darkness and silence. Another, more dramatic idea is the Big Rip. If dark energy keeps growing stronger, it might eventually overcome all other forces, not just pulling galaxies apart, but tearing stars, planets, and even atoms themselves into nothingness. And then there's the Big Crunch, the opposite outcome. If dark energy were to reverse or weaken, gravity could someday win. The universe would slow, stop, and then collapse back into itself, ending as violently as it began. Right now, NASA's data suggests we're heading for the Big Freeze. The cosmos will keep stretching, growing colder and lonelier, with the edge of the observable universe racing away faster than light. But every new discovery could change that prediction. Dark energy doesn't make itself known easily. It doesn't emit light or radiation. It doesn't interact with matter in any measurable way. So NASA scientists look for its fingerprints in the patterns of galaxies, the brightness of distant supernovae, and the slight distortions in the CMB. One of NASA's most powerful tools for this is gravitational lensing. When the light from a distant galaxy bends around a massive object, like another galaxy or a cluster. By studying how that light bends, scientists can map how matter is distributed through space. And the more precisely they can map matter, the more clearly they can see the invisible hand of dark energy pushing it all apart. The Hubble Space Telescope has captured hundreds of these gravitational lenses. Each one acts like a magnifying glass, offering a glimpse deeper into the past. Meanwhile, the James Webb Space Telescope is going even further, detecting the faintest galaxies formed just a few 100 million years after the Big Bang. Together, they create a 3D map of cosmic evolution, a way to trace how dark energy's influence has changed over billions of years. This combination of Hubble and JWST data has already revealed something strange. Early galaxies appear far more massive and mature than they should be, given how young the universe was. It's forcing scientists to question whether dark energy behaved differently in the past, or whether something entirely new is at play. NASA isn't stopping there. To truly understand dark energy, it's building the Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s. Roman will have a field of view 100 times larger than Hubble's and will be designed specifically to study dark energy. It will measure the shapes, distances, and brightness of millions of galaxies, creating the most detailed cosmic map ever made. By tracking how galaxies cluster and move over time, Roman will help determine whether dark energy is constant or changing, and whether it's connected to new laws of physics. In a sense, Roman will act as a cosmic time machine, showing how dark energy shaped everything from the first stars to the ultimate destiny of the cosmos. Every discovery about dark energy changes our understanding of what the edge of the universe even means. The more we look, the faster the edge moves away. The observable universe is now about 93 billion light-years across, but that number keeps growing, not because light travels faster, but because space itself keeps expanding. NASA's instruments aren't just mapping the edge, they're chasing it, trying to catch something that can never be reached. Each time we build a better telescope, we see farther into the past, but the boundary always slips further away. Dark energy is what makes that boundary move. It's the force stretching the fabric of the cosmos, pushing galaxies beyond the horizon of visibility. And in doing so, it's showing us that the edge of the universe isn't a wall, it's a horizon, always receding, always just out of reach. That realization changes everything. It means the universe is not just bigger than we thought, it's stranger. NASA's quest to understand dark energy isn't just about numbers and measurements. It's about confronting the most profound mystery of all, why the universe exists the way it does. If dark energy were even slightly stronger or weaker, life might never have formed. Galaxies might not exist. Stars might never have lit up. The balance is so precise it feels almost impossible, a cosmic knife's edge that separates being from nothing. Every new discovery brings us closer to understanding that balance. Yet the closer we get, the more the universe seems to whisper, "You've only just begun to understand me." Maybe dark energy isn't something to be solved. Maybe it's the universe's way of keeping some secrets to itself, ensuring that even as we reach for the edge, there's always more to discover. Because in the end, NASA's journey to understand dark energy isn't just about space. It's about us. It's about the human desire to explore, to ask why, and to keep pushing forward, even when the answers lie hidden in the dark. And perhaps that's what makes this mystery so powerful. The more we learn, the more we realize how small we are. And yet how remarkable it is that we can look out across billions of light years and dare to ask, what's really out there? The edge of the universe isn't a place, it's a pursuit. And thanks to NASA, we're chasing it faster than ever before. Observing the first galaxies, the earliest cosmic structures. In the beginning, there was darkness. The young universe, only a few 100 million years old, was filled with a hot, dense fog of hydrogen gas. No stars yet burned, no galaxies yet shone. The cosmos was silent, waiting for the first sparks of light to ignite. For billions of years since, that ancient light has been traveling across the universe, stretched, dimmed, and warped by time and distance, until it finally reaches us. And now, for the first time in human history, NASA's telescopes are powerful enough to catch it. Every faint glimmer that NASA captures from the farthest reaches of space is more than a picture. It's a time machine. The farther we look, the further back in time we go. And at the very edge of what we can see lies the story of creation itself, the birth of the first galaxies. After the Big Bang, the universe expanded rapidly and cooled. For about 380,000 years, it was filled with a glowing plasma, particles of matter and light constantly colliding. Eventually, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. This ancient glow, known as the cosmic microwave background, CMB, marks the earliest light we can detect. But after that first light, darkness fell again. For hundreds of millions of years, there were no stars, just vast clouds of hydrogen gas drifting in the cosmic dark. Astronomers call this era the Cosmic Dark Ages. Then something extraordinary happened. Tiny ripples in that gas, the leftover fingerprints of quantum fluctuations from the Big Bang, began to attract matter through gravity. The densest regions drew in more and more gas, collapsing under their own weight until nuclear fusion ignited. The first stars were born. These stars were nothing like the ones we see today. They were enormous, hundreds of times more massive than our Sun, and burned through their fuel quickly, exploding as supernova after just a few million years. Their violent deaths scattered heavy elements into space, creating the raw material for new generations of stars and planets. As these stars formed in clusters, they pulled together into larger systems. Gravity stitched them into swirling, luminous structures, the first galaxies. For decades, these first galaxies were invisible. They were too faint, too far, and too red-shifted for any telescope to detect. But NASA's space telescopes changed everything. The Hubble Space Telescope, launched in 1990, was humanity's first major leap towards seeing deep into cosmic history. Its observations, especially the famous Hubble Deep Field and Ultra Deep Field images, revealed thousands of galaxies in what looked like an empty patch of sky. Many of those galaxies were so distant that their light had been traveling for over 13 billion years. To the human eye, they appeared as tiny smudges, but to astronomers, they were ancient fossils, galaxies from a time when the universe was still in its infancy. Each galaxy's distance can be measured using a concept called redshift. Because the universe is expanding, light from distant objects is stretched toward longer, redder wavelengths. The higher the redshift, the older and farther away the galaxy is. Hubble detected galaxies with redshifts around Z equals sign 10, which means the light left those galaxies just 500 million years after the Big Bang. That was groundbreaking, but it was only the beginning. Then came NASA's new eyes, the James Webb Space Telescope, JWST. When JWST launched in December 2021, its mission was clear: to look deeper and farther than any telescope before it. Unlike Hubble, which observes mostly visible light, JWST is designed to see infrared light, the kind of light that ancient galaxies emit after billions of years of redshifting. Infrared vision allows JWST to peer through cosmic dust, revealing hidden structures and ancient stars invisible to other telescopes. Within months of its first full-color images being released, JWST was already breaking records. It spotted galaxies at redshifts greater than Z equals sign 13, meaning they formed just 300 million years after the Big Bang. Some evidence even hints at galaxies existing around Z equals sign 1416, which would place them only 250 million years after the Big Bang, almost unimaginably early. To put that in perspective, if the entire history of the universe were a single year, JWST is showing us galaxies forming just 1 week after the cosmic New Year's Day. These discoveries shocked astronomers. The galaxies JWST found were far brighter and more massive than expected. In such a young universe, there shouldn't have been enough time for so many stars to form, or for galaxies to grow that large. NASA's scientists began to ask, were the first galaxies forming faster than we thought? Or is our entire understanding of the early universe incomplete? Every time NASA announces a new record-breaking galaxy, The number that captures everyone's attention is its redshift. But redshift isn't just a distance marker. It's a story about time and motion. The universe is expanding, stretching the light from distant galaxies like a rubber band. If you imagine light waves as ripples on water, expansion makes those ripples longer and slower. That's why faraway galaxies appear redder. Their light has been stretched by billions of years of cosmic growth. By measuring that stretch, astronomers can calculate how far away and how old a galaxy is. Hubble could measure redshifts up to around Z equals 10, but JWST's infrared sensors extend that range far beyond, allowing it to detect galaxies at Z equals 15 or higher. That's like opening a new chapter in a book we didn't even know existed. And with every new observation, JWST and NASA scientists are finding that the early universe was more active, more crowded, and more structured than anyone expected. Among the most remarkable NASA discoveries is a galaxy called Glass Z13, found by JWST. It dates to roughly 13.4 billion years ago, just 300 million years after the Big Bang. That makes it one of the oldest galaxies ever observed. Another candidate, Sears 93316, may be even older, its light possibly dating to only 240 million years after the Big Bang. These galaxies are so faint that detecting them requires deep field observations lasting over 12 hours. Long exposures that capture the faintest glimmers of infrared light from across the cosmos. What's fascinating is not just their age, but their appearance. Even at such young ages, these galaxies seem surprisingly mature. They contain billions of stars, structured disks, and even hints of spiral formations, features scientists didn't expect to see until billions of years later. This challenges everything we thought we knew about cosmic evolution. If these galaxies truly existed so early, it means star formation began almost immediately after the universe's dark ages ended. Somehow, the universe went from total darkness to fully formed galaxies in less than 300 million years, an astonishingly short time in cosmic terms. Every early galaxy NASA observes is like a page from the universe's autobiography. Their light tells us how quickly stars formed, how matter gathered, and how the first structures took shape. From JWST's data, astronomers have learned that early galaxies were far smaller than modern ones, often just a fraction of the Milky Way's size. But they were also far denser and brighter, filled with hot, massive stars that lived short, violent lives. These stars flooded the universe with ultraviolet radiation, ending the cosmic dark ages in an event known as reionization. Reionization was a cosmic transformation. The intense radiation from the first stars and galaxies stripped electrons from hydrogen atoms, making the universe transparent for the first time. NASA's telescopes can now see evidence of this transition in the faint glow of distant galaxies. In a sense, these galaxies didn't just light up the universe, they changed its physics. And NASA can determine the chemical fingerprints of these ancient galaxies by studying their light spectra. Surprisingly, many of them already contain heavy elements like carbon, oxygen, and iron, elements that shouldn't exist in large quantities so soon after the Big Bang. This means the first generations of stars must have formed, lived, and exploded incredibly fast, enriching the cosmos with the ingredients for new worlds. NASA's role in rewriting cosmic history. Before JWST, scientists believed galaxy formation was a slow, gradual process. The first small structures would merge over billions of years to form larger galaxies like the Milky Way. But NASA's discoveries are painting a very different picture, one of rapid, chaotic evolution. Galaxies appear to have assembled far earlier and grown far faster than expected. Some even show signs of supermassive black holes at their centers, black holes that would require an almost impossible growth rate in such a short time. This has forced cosmologists to revisit their models of the early universe. Maybe the first stars were more massive than we thought. Maybe dark matter clumped together faster. Or maybe there's something deeper we still don't understand about how gravity shaped those early times. NASA's telescopes aren't just answering questions, they're raising new ones. As JWST continues scanning the skies, NASA teams are identifying hundreds of new galaxy candidates every month. Each one is a potential window into the past, a chance to push the boundary of the observable universe even further. With every observation, NASA is refining the timeline of cosmic history, turning what was once theory into vivid infrared reality. And beyond JWST, future missions like the Nancy Grace Roman Space Telescope will expand that map even further, capturing millions of galaxies in a single field of view. Together, they're building a story that stretches across all of time, from the faint flicker of the first stars to the sprawling galaxies we see today. The most striking part of that story? It's that the universe became organized, beautiful even, astonishingly fast. Against all odds, order rose out of chaos. Within a few 100 million years, stars were shining, galaxies were swirling, and the universe had already begun shaping itself into the vast cosmic web we live in now. When NASA scientists look at the faint light from those early galaxies, they're not just studying ancient stars, they're witnessing creation itself. Each photon of light carries a message from the dawn of time, whispering how the universe grew from nothing into everything. And as that message travels billions of years to reach our instruments, it reminds us of something profound. The universe isn't a static thing. It's alive, changing, evolving. The galaxies we see at the edge of the observable universe aren't just relics of the past. They're the ancestors of everything that exists today. Every atom in our bodies, every planet, every star. All of it began in those first bursts of light. That's what makes NASA's discoveries so powerful. They're not just scientific milestones. They're chapters in our own story. When we look at those first galaxies, we're looking at our origins, the moment the universe began to see itself. And perhaps the most beautiful truth of all is that the story isn't finished. Every time NASA looks deeper, the edge moves further away. Every new galaxy we find pushes the boundary of what's known, reminding us that the universe is still expanding, still creating, still becoming. The first galaxies were the universe's first words, and now, across billions of years, we're finally learning how to read them. Exoplanets and cosmic neighborhoods. When you look up at the night sky, every star seems like a tiny, distant spark. But what if almost every one of those stars had planets orbiting around it? Worlds of rock, gas, or even water hidden in the darkness. For most of human history, this question was a dream of imagination. We didn't know if planets existed beyond our solar system. We didn't even have proof that other suns could host their own families of worlds. That mystery lasted until NASA decided to find out. Today, the discovery of planets beyond our solar system, known as exoplanets, has completely changed how we see the universe. It's no longer a cold, empty void sprinkled with stars. It's a cosmic neighborhood full of potential homes, each one carrying its own story, its own chemistry, its own chance for life. And NASA has been the one unlocking that door. It started with a question so big it almost felt philosophical. Are we alone? NASA's scientists knew that to answer that question, they needed to go beyond our solar system. They had to find planets orbiting other stars, worlds that might look a little like Earth, bathed in the right kind of starlight, where water could flow and life might take hold. But how do you find something smaller than a speck of dust, hidden in the blinding glare of a star billions of times brighter? It seemed impossible. Planets don't shine on their own. They only reflect the faint glow of their parent star. Detecting one was like spotting a single firefly fluttering in front of a floodlight, from thousands of miles away. For decades, the search seemed hopeless. Astronomers could guess, they could model, but they couldn't see. Until technology finally caught up with curiosity. And then, in 2009, NASA launched a spacecraft that changed everything. The Kepler Space Telescope was more than an instrument. It was a bold statement. Its job was to stare at one patch of sky for years on end, watching over 150,000 stars at once, looking for something incredibly subtle, a tiny temporary dimming of light. That dimming, known as a transit, happens when a planet passes in front of its star, blocking just a fraction of its light. For a Sun-like star, that dip might only be 0.01%. But Kepler was sensitive enough to notice it. It could spot planets smaller than Earth from hundreds of light years away, all by catching these minuscule shadows. At first, even NASA's own teams weren't sure if it would work. The signal was so faint that even the smallest vibration or software error could ruin the data. But when the first light data came back, the results were breathtaking. Kepler didn't just find one planet, it found hundreds, then thousands. Within a few short years, Kepler revealed that planets are everywhere. They're not rare at all, they're the rule, not the exception. Almost every star in the sky likely hosts at least one planet. This single realization completely rewrote humanity's understanding of the cosmos. The Milky Way alone may contain hundreds of billions of planets, and that's just our galaxy. Among the thousands of worlds Kepler discovered, a few stood out. They were small, rocky, and orbiting in a region scientists call the habitable zone, the distance from a star where liquid water could exist on the surface. These were Earth's cosmic cousins. One of the most famous was Kepler, 452b, often nicknamed Earth's older, bigger brother. Located about 1,400 light-years away, it orbits a Sun-like star and sits in the sweet spot for possible habitability. Another, Kepler 22b, became a symbol of hope, a potential world with mild temperatures and maybe even oceans. But Kepler's most astonishing revelation wasn't a single planet. It was the bigger picture. There are likely billions of potentially habitable worlds in our galaxy alone. That means somewhere out there, under an alien sun, oceans could be glistening. Rain might fall on distant soil, and maybe, just maybe, something could be looking back. Kepler had changed everything, but like all great explorers, it had limits. It focused on one narrow patch of sky and eventually lost its ability to maintain its orientation due to mechanical issues. NASA needed a new generation of planet hunter, one that could look everywhere. That's where TESS came in, the Transiting Exoplanet Survey satellite, launched in 2018. If Kepler was like a telescope peering through a keyhole, TESS was like throwing open the entire door. Instead of staring at one field, TESS scans nearly the whole sky, observing the brightest, nearest stars. Its mission was to find planets close enough for future telescopes, like the James Webb Space Telescope, to study in detail. Within months, TESS started uncovering treasures: strange, scorching hot super-Earths, dense mini-Neptunes, and even multi-planet systems orbiting stars visible to the naked eye. TESS showed us that the universe isn't just filled with planets, it's filled with variety. Some worlds orbit so close to their stars that a year lasts only a few days. Others drift farther out, where it's colder than Pluto. Some may be covered entirely in oceans. Others might have skies of methane or rain made of molten glass. Every discovery stretched our imagination of what a planet could be. Then came the James Webb Space Telescope, JWST, the most powerful observatory ever built. While Kepler and TESS could detect planets, they couldn't tell us what those worlds were like. JWST was designed to change that. With its giant gold-coated mirrors and infrared instruments, JWST can do something no telescope before it could. It can analyze the atmospheres of exoplanets. Here's how it works. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere. JWST captures that light and breaks it down into a spectrum, a kind of chemical fingerprint. By studying the colors that are absorbed or emitted, scientists can tell what gases are present: oxygen, carbon dioxide, methane, water vapor, and more. And that's where things get truly exciting, because those gases can hint at habitability, or even life. In 2023 and 2024, JWST started delivering its first exoplanet spectra, and the results were astounding. It detected carbon dioxide on a planet 700 light-years away, water vapor in the skies of a hot Jupiter, and methane on others. It even observed clouds made of silicates, the same material found in sand and glass, floating in alien skies. These discoveries were more than data points. They were glimpses into living worlds, real, physical places orbiting stars we can barely see, each one carrying the potential for chemistry, weather, and maybe even biology. For years, scientists dreamed of going even further, beyond the Milky Way itself. Could there be planets in other galaxies, orbiting distant suns we can't even resolve? In 2021, NASA's Chandra X-ray Observatory may have found the first evidence. Chandra observed a star system in a galaxy 28 million light-years away and detected a dip in X-ray emissions, possibly caused by a planet-sized object passing in front of its host. If confirmed, this would be the first extragalactic planet ever discovered, a world orbiting not just another star, but in another galaxy entirely. It's an astonishing reminder of how small we are and how endless the universe truly is. Every exoplanet discovery brings us closer to understanding our place in the cosmos. Some are hostile gas giants or molten worlds where metals rain from the sky. Others orbit faint red dwarfs that could glow dimly for trillions of years, long after our sun dies. But the most haunting thought is this: the universe might be teeming with planets like ours. NASA's ongoing missions, Kepler's legacy, TESS's skywide survey, and JWST's detailed analysis are painting a new picture of the cosmos. It's not an empty expanse, but a living, dynamic community of worlds. Some may have oceans, some may have clouds, some may even have something watching their own night skies, wondering if they're alone too. Signs of life, the search for biosignatures and alien atmospheres. Finding a planet is one thing, but finding a planet alive, that's the dream. That's the question that has haunted humanity for centuries, whispered through telescopes and woven into our stories. Are we alone? For NASA, that question isn't just about curiosity, it's about identity. Because if even one other world out there breathes, it means the universe isn't empty. It means life isn't an accident, it's a pattern. But life, as fragile as it is, doesn't leave an obvious signature in the stars. We can't see alien forests or oceans from across the galaxy. What we can see are traces, the fingerprints of biology written in the air of distant worlds. And that's where NASA's search has entered its most thrilling chapter, the hunt for biosignatures. A biosignature is any detectable sign of life. It doesn't have to be a picture of an alien creature waving from a crater. It can be something much subtler, a combination of gases, chemicals, or even colors that can't easily exist without biological activity. On Earth, the air itself is one giant biosignature. Our atmosphere is filled with oxygen, a gas constantly replenished by plants and microorganisms. Without life, it would vanish in a matter of centuries, chemically consumed by rocks and other reactions. The same goes for methane, which seeps from biological processes deep underground and from the stomachs of animals. What's fascinating is that these gases alone aren't proof of life, but when found together, in the right balance, they become highly suspicious. Oxygen and methane shouldn't coexist in large amounts. One destroys the other. The fact that both thrive in our atmosphere is like a neon sign flashing, something alive is maintaining this equilibrium. So NASA's task is clear: find those signs on other worlds. Detecting a planet's atmosphere from light years away sounds impossible, but it's already happening. When a planet passes in front of its star, a transit, a tiny fraction of the starlight filters through the planet's atmosphere. That light carries clues about what gases it passed through. NASA's telescopes capture that filtered light and split it into its spectrum, the rainbow fingerprint that reveals chemical identities. Certain wavelengths are absorbed or emitted by specific molecules, leaving unique signatures scientists can read like a code. From this technique, NASA has already found evidence of water vapor, carbon dioxide, methane, ammonia, and even clouds made of exotic materials like metal oxides. Each discovery sharpens our ability to read the skies of other worlds. But the next step is the hardest: finding atmospheres that look alive. To search for alien life, NASA first had to understand what makes Earth so distinctive from space. Imagine observing Earth as if it were an exoplanet. The first thing you'd notice is that its color changes: blue oceans, green continents, white clouds. The atmosphere absorbs light at specific wavelengths due to oxygen and ozone. Infrared sensors would detect water vapor and carbon dioxide, and subtle spectral features would hint at vegetation, the famous red edge, a spike in reflectivity caused by plant chlorophyll. These are the exact fingerprints NASA is now hunting for on other worlds. To perfect that search, NASA has used Earth as its own test subject. Satellites like Aqua, Aura, and Suomi NPP have studied our planet's atmosphere from orbit, while missions like OSIRIS-REx and MAVEN have helped scientists compare Earth's chemistry to barren neighbors like Mars and asteroids. By understanding what a living world looks like, NASA has built the playbook for recognizing another. The James Webb Space Telescope is now at the forefront of this quest. While earlier telescopes could detect planets and identify some gases, JWST's sensitivity allows it to peer much deeper into atmospheric layers. When it observes a transiting planet, it can detect even tiny traces of gases like ozone or methane. It can also measure temperature and pressure profiles, giving scientists a sense of whether the planet has stable conditions for life, winds, clouds, and even climate cycles. In 2023, JWST made headlines when it detected carbon dioxide and water vapor in the atmosphere of a planet called K218b, located 120 light-years away. But it was something else in that data that sent ripples through the scientific community: a potential signal of dimethyl sulfide, DMS, a molecule that, on Earth, is produced almost entirely by living organisms, specifically marine phytoplankton. It's far too early to declare the presence of life, and NASA's scientists are cautious. But even the possibility that such a molecule could exist so far away is breathtaking. It's the first real taste of what the next decade of exploration might uncover. Finding a gas isn't enough. NASA knows that every potential biosignature has to be weighed carefully. There are false positives, non-biological processes that can mimic the signs of life. Volcanoes, for example, can produce methane. Ultraviolet radiation can split carbon dioxide into oxygen. That's why NASA's scientists always look for context. They study the planet's temperature, its star type, and its atmosphere's chemical balance. A small rocky planet with oxygen orbiting a stable star might be a good candidate, but a similar signal from a hot, unstable star could be misleading, created by photochemical reactions instead of biology. This contextual analysis, figuring out whether chemistry can be explained without life, is a discipline NASA calls astrobiology. It's where chemistry, biology, and planetary science collide. And it's where some of NASA's most creative minds are working to develop a biosignature checklist, a framework for deciding when a planet's data is too coincidental to ignore. While telescopes search for life far beyond our reach, NASA's robots are exploring closer frontiers, worlds within our solar system that could harbor life today. Mars, for instance, has been the subject of intense exploration for decades. The Perseverance rover is currently drilling into Martian rocks, searching for ancient microbial fossils. Its data will eventually be returned to Earth through a future sample return mission, perhaps the first time we'll hold material from another planet that could show evidence of past life. Meanwhile, NASA's Europa Clipper, launching soon, will explore Jupiter's moon Europa, an icy world hiding a vast ocean beneath its frozen surface. Plumes of water have been seen spraying into space, and the spacecraft will fly through them, analyzing their chemistry for organic molecules or potential biosignatures. And then there's Enceladus, Saturn's mysterious moon. Its geysers, captured by the Cassini spacecraft, shoot water, salt, and complex carbon compounds into space, materials that suggest an active hydrothermal system below the ice. Some scientists believe Enceladus could be one of the most promising places for microbial life in the solar system. These missions remind us that the search for life isn't limited to distant exoplanets. It's happening right here in our own backyard. While NASA's main focus is finding biological life, there's another frontier quietly emerging: the hunt for technosignatures, signs of advanced civilizations. Unlike biosignatures, which come from natural life processes, technosignatures could be the byproducts of technology: radio signals, laser pulses, industrial chemicals, or even unusual heat patterns. NASA isn't directly running alien hunting programs, but it supports research in this area through grants and partnerships with the SETI Institute and university teams. They're looking for patterns that nature can't easily explain, like narrowband radio signals or chemical imbalances that suggest pollution. One intriguing example: certain chlorofluorocarbons which humans produce could theoretically be detected in the atmosphere of another planet. If JWST or future telescopes ever found such molecules, it would raise serious questions. Who or what put them there? For now, that remains in the realm of possibility, not proof. But the technology to look for it is finally within reach. One of the biggest challenges in NASA's search is defining what life actually means. For all our exploration, we only have one known example: Earth. Every hypothesis, every model, every hope is built on that single data point. But what if life elsewhere doesn't follow the same rules? Maybe it doesn't rely on water. Maybe it doesn't breathe oxygen or use carbon as a base. Maybe it thrives in methane lakes, like those on Titan, Saturn's largest moon, where NASA's upcoming Dragonfly mission will land and explore. NASA's scientists are keeping their definitions open. They talk not only about life as we know it, but also life as we don't know it. That means developing instruments capable of detecting a wide range of organic chemistry. Not just our familiar blue and green version, but alien biologies that might look, move, or function in completely different ways. The search for life isn't just scientific, it's philosophical. It's forcing us to rethink what it means to be alive. For the scientists working on these missions, the search isn't just data, it's deeply personal. Every signal, every spectrum, every new image carries the possibility of rewriting what it means to be human. They know that one day they might look at a graph, just a dip in light, a curve of color, and realize they're seeing the breath of another world. And if that happens, it won't just be NASA's discovery. It will be humanity's. Because the moment we find another world that's alive, everything changes. The boundaries of solitude dissolve. The night sky stops being distant. It becomes shared. As the next generation of telescopes and missions comes online, NASA's search for biosignatures will only intensify. Future observatories will combine visible infrared and ultraviolet instruments to scan thousands of exoplanets. Some will look for the subtle glint of oceans. Others for the rhythmic pulse of seasonal change, signs that a planet might be cycling through life and death, just like Earth. Machine learning and artificial intelligence are also becoming part of the search, helping NASA sift through terabytes of spectral data for patterns no human could spot. And somewhere in that data, maybe next year, maybe in a decade, there could be a signal that makes history. Not a voice, not a message, but a whisper of chemistry that says quietly and clearly, "You are not alone." Cosmic anomalies and mysteries. At the edge of the observable universe, things start to get strange. The deeper NASA looks, the less the cosmos behaves the way we expect it to. Galaxies that shouldn't exist yet, vast regions almost completely empty, and mysterious alignments stretching across billions of light years. All of it whispers the same unsettling truth. The universe is not just bigger than we imagine. It's stranger than we can comprehend. When we first looked out into space, we thought the universe was sprinkled with galaxies like stars scattered across the night sky. Random, endless, evenly spaced. But the more NASA's telescopes mapped the cosmos, the clearer it became that the universe wasn't random at all. It had structure, enormous structure. Instead of being evenly distributed, galaxies gather into superclusters, massive collections of thousands of galaxies bound together by gravity. These superclusters stretch for hundreds of millions of light years, forming the largest known objects in the universe. And between them, vast cosmic deserts called voids, where almost nothing exists. No stars, no gas, just darkness and silence. Imagine a web, a vast glowing spiderweb made of galaxies instead of silk. That's what the universe looks like on the largest scale. Astronomers call it the cosmic web, a network of filaments where matter clusters, forming highways of galaxies that connect the universe together. It's beautiful and deeply unsettling, because no one fully understands why it looks that way. NASA's maps, drawn from deep space surveys using telescopes like Hubble and the Chandra X-ray Observatory, revealed these filaments in exquisite detail. The Milky Way itself is just a single thread in this cosmic tapestry, tucked inside a supercluster called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is home to over 100,000 galaxies, stretching over 500 million light-years across. And it's still just one small part of something bigger. Between the threads of the cosmic web lie the voids, enormous, lonely regions that make up most of the universe's volume. Some of these voids are hundreds of millions of light-years wide. They're so empty that if you dropped the entire Milky Way into one, it would be swallowed by darkness. But these voids aren't just empty space. They may hold clues about the hidden forces shaping the cosmos. NASA's WMAP and Planck missions, which mapped the cosmic microwave background, the afterglow of the Big Bang, found subtle temperature differences that align suspiciously with some of these voids. One region, known as the cold spot, stands out, a patch of the universe that's significantly cooler and emptier than it should be. No one knows exactly why it exists. Some theories suggest it's a giant supervoid, an enormous region, almost devoid of galaxies. Others whisper something more dramatic, that it might be the fingerprint of another universe brushing against ours. If that's true, then our cosmos might not be alone. As NASA's telescopes gathered more data, something even stranger emerged, an unexpected pattern in the universe's deepest structures. Across billions of light-years, galaxies and quasars, the hyper-bright hearts of ancient galaxies, seem to align along invisible axes, like beads on a string stretched across the cosmos. One of the most famous of these is known as the Axis of Evil, a mysterious alignment first discovered in the data from NASA's WMAP mission and later confirmed by the Planck satellite. The name might sound dramatic, but it fits the mystery. The cosmic microwave background, the oldest light in the universe, should be random and chaotic. Instead, its temperature fluctuations seem to line up in one direction. It's as if the universe itself has a preferred orientation, something that shouldn't be possible in a truly random isotropic cosmos. Could this be a flaw in our data, a statistical coincidence? Or is there something deeper, a hidden structure or force guiding the shape of the universe itself? NASA scientists don't have a definitive answer, but the implications are enormous. If the universe does have a built-in direction, it could rewrite everything we know about the Big Bang, cosmic inflation, and the fundamental symmetry of space itself. The deeper NASA peers into space, the more galaxies are found that simply should not exist. Some galaxies appear too old for their distance. According to our current understanding, looking deeper into space means looking back in time. So galaxies at extreme distances should appear young, chaotic, and undeveloped. But telescopes like Hubble and the James Webb Space Telescope, JWST, have found ancient-looking galaxies existing just a few 100 million years after the Big Bang. Galaxies that are far too massive, far too structured, and far too bright for their age. It's as if the universe built them overnight. NASA's data stunned cosmologists. These galaxies, nicknamed impossible galaxies, have forced scientists to question their models of cosmic evolution. Some are 10 times more massive than expected, filled with mature stars and complex structures that shouldn't have had time to form. How did they come to be so fast? Are our estimates of time and distance slightly off? Or are we missing something fundamental about how matter assembles after the Big Bang? JWS, with its infrared eyes, keeps finding more of them, galaxies that seem to exist before they should. Each discovery adds another twist to the cosmic puzzle. Another mystery comes from the strange brightness seen in some distant regions of the universe. NASA's observations revealed galaxies and quasars that shine brighter than theory allows. So bright they should have burned out or collapsed long ago. Some scientists think these could be powered by enormous black holes that grew far faster than expected, swallowing matter and spitting out radiation. Others think we might be witnessing gravitational lensing, the bending and magnification of light by massive objects between us and the source. But even lensing doesn't explain everything. Some distant galaxies seem to shine without any clear cause. It's as though there's extra light in the universe, light that shouldn't exist. NASA's New Horizons spacecraft, far from Earth and beyond Pluto's orbit, even detected a faint background glow that can't be traced to any known source. It's not starlight, not reflected sunlight, not dust. It's something else. A subtle shimmer in the cosmic dark, coming from nowhere and everywhere at once. Scientists call it the cosmic optical background, but what it really represents, nobody knows. In 2008, NASA's researchers noticed another oddity: entire clusters of galaxies drifting in the same direction at incredible speeds, as if pulled by something unseen beyond the observable universe. They called it the dark flow. Galaxies thousands of light years apart, spread across vast regions of space, all seem to be moving toward a single point, a mysterious gravitational source that shouldn't exist within our visible cosmos. Some scientists speculated it could be the gravitational tug of a supermassive structure outside the observable boundary, something larger than anything we can detect. Others suggested it might be an illusion caused by uneven expansion of space itself. Whatever the cause, the dark flow remains one of NASA's most haunting discoveries. Because if it's real, it hints that our universe may be part of something far bigger, a cosmic ocean where our visible universe is just one wave among many. When people talk about the edge of the universe, they often imagine a wall, a boundary, or a final horizon. But the more NASA looks outward, the more it becomes clear. There is no edge, at least not in the way we think. Space doesn't just end, it stretches, curves, and folds. What we call the edge is really a limit of perception, a place where light from beyond hasn't had enough time to reach us. The universe could go on forever, or it could curve back on itself like the surface of a sphere. And that realization changes everything. Because when NASA peers toward that invisible boundary, when telescopes like JWS catch the faintest glimmers of ancient light, we're not just looking at the past, we're staring at the limit of human knowledge itself. What lies beyond? More galaxies? Other universes? Or something our minds simply can't describe yet? The truth is, the universe still keeps its secrets close. Every time NASA answers one question, 10 more appear. The cosmic web, the voids, the alignments, the impossible galaxies, each one challenges our understanding of reality. Maybe that's the point. Maybe the universe isn't meant to be neatly explained. Maybe its mysteries exist to remind us how little we really know, and how much more there is to discover. Because at the edge of the universe, science and wonder become the same thing. And that's where NASA is looking next. The axis of evil and other cosmic oddities. For decades, scientists believed the cosmos was smooth and uniform on the largest scales, that if you zoomed far enough out, everything would even out. The Big Bang, they thought, sent energy and matter flying in all directions equally. No side of the universe should be special. No direction should stand out. But when NASA began mapping the oldest light in existence, the afterglow of the Big Bang itself, that assumption began to crumble. In 2003, data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, revealed a subtle but undeniable pattern etched across the sky. It wasn't a galaxy or a nebula or any object at all. It was a faint alignment buried within the cosmic microwave background, the ghostly radiation left over from the universe's birth. This background light should have been random, like static on a television screen. Instead, certain temperature fluctuations appeared to line up along a single axis that cut across the universe. It was as if the entire cosmos had a preferred direction, a cosmic tilt that made no sense. Scientists, half in awe and half in disbelief, began calling it the axis of evil. The name came partly from frustration, because the discovery wasn't supposed to exist, and partly from the quiet fear that something fundamental about cosmology might be wrong. This strange alignment seemed to mock everything we thought we knew about the shape and behavior of the universe. If space itself had a direction, that would shatter one of the most important ideas in cosmology. Isotropy, the assumption that the universe looks the same no matter where you look. The data was checked again and again. Was it a glitch, a trick of the instruments, something caused by the Milky Way's foreground radiation? Yet each new mission, first WMAP, then the European Space Agency's Planck satellite, working in partnership with NASA, confirmed the same unsettling signal. The alignment was real, and it stretched across billions of light years. The early universe itself, in its faint leftover glow, appeared to be pointing somewhere. For years, NASA scientists and cosmologists debated what it meant. Some suggested that the axis of evil was a sign of new physics, a clue that the Big Bang had not been perfectly symmetric. Others thought it might be evidence of something beyond our observable universe, perhaps another cosmos brushing against our own, leaving a faint directional imprint on the sky. There were even more radical ideas, that space itself might be shaped like a dodecahedron, a 12-sided figure, giving the illusion of alignment when viewed from inside. But the problem didn't end there. The more NASA looked, the more other cosmic oddities began to appear, hints that the universe might be hiding layers of structure that break the rules we thought were absolute. One of these was a mysterious pattern in the distribution of quasars, the blazing hearts of young galaxies powered by supermassive black holes. When their light was mapped across the sky, it too seemed to align in strange ways, almost echoing the same orientation as the axis of evil. It was as if something far beyond human scale was pulling strings across the universe, guiding galaxies, quasars, and even background radiation into invisible harmony. This kind of cosmic order wasn't supposed to exist. Gravity alone couldn't explain it. The equations describing the early universe couldn't explain it. Yet the evidence kept stacking up. A strange sense of design, or at least direction, haunted the data. In 2013, the Planck mission delivered the most precise map ever made of the cosmic microwave background. And there it was again. That same alignment, clear and undeniable. Planck's instruments were more advanced than any before it, and the patterns it saw weren't easily dismissed. The signal was faint, yes, but persistent. For scientists, it was a humbling moment. After decades of believing the universe had no preferred direction, here was something that suggested otherwise. The question wasn't just why it existed, but what it might mean for everything else. One theory that grew in popularity proposed that the axis of evil might be the result of a massive, unseen structure far beyond our cosmic horizon, something pulling on space-time itself. NASA's data on galactic flows, including the puzzling motion known as dark flow, seemed to echo that possibility. Clusters of galaxies across huge regions of space all appeared to be moving toward the same point, as though tugged by an invisible hand from outside the observable universe. If that's true, it would mean our universe isn't a closed system at all. It might be just one bubble in a far larger multiverse, with other universes exerting gravitational influence across cosmic boundaries. To many scientists, that sounded absurd, too speculative, too grand. But the problem was that no simpler explanation fit the data. The more refined the measurements became, the clearer it was that something was off. Even the rotation of galaxies and the orientation of certain cosmic filaments seemed to hint at large-scale coherence, patterns that shouldn't be there if the universe were truly random and isotropic. NASA's missions, meanwhile, kept pushing forward. The Chandra X-ray Observatory mapped the hot plasma threading between galaxies, showing how energy flowed through the cosmic web. The Hubble Space Telescope captured gravitational lenses, massive galaxies bending light from objects behind them, and revealed alignments that matched larger cosmic patterns. And then the James Webb Space Telescope added another layer, peering so far back in time that it began catching glimpses of the universe when it was less than 1 billion years old. Even there, in that chaotic infancy, some of the same directional biases seemed to persist. It was becoming harder and harder to shrug it off as coincidence. If the axis of evil and other cosmic alignments are real, they may force science to reconsider the deepest assumptions about reality. Perhaps space isn't perfectly smooth. Perhaps the Big Bang wasn't entirely uniform. Or perhaps there's a hidden structure woven into the fabric of the cosmos, something older and larger than the universe we know, an imprint left by a previous cycle of creation, or the faint echo of another universe colliding with ours in the earliest moments of time. The idea of a multiverse, once the realm of philosophy and science fiction, suddenly didn't seem so far-fetched. NASA's observations of cosmic microwave background irregularities, the dark flow, and large-scale alignments all began to look like possible hints that our universe might not be alone. If space is infinite, then somewhere beyond the observable horizon could exist other regions with their own laws of physics, their own galaxies, even their own versions of reality. The boundaries between them might occasionally brush together, leaving marks, cold spots, directional tilts, unexplained flows, the faint fingerprints of cosmic neighbors. Still, not everyone agrees. Some scientists insist the axis of evil might simply be an artifact, a trick of data processing or contamination from the Milky Way's dust. The Planck team, for instance, spent years trying to remove galactic interference, yet the alignment stubbornly remained. Others argue that our human brains, so wired for patterns, might be finding meaning where none exists. But that explanation feels less satisfying the more evidence piles up from independent missions. The search for answers continues through NASA's newer projects. The Nancy Grace Roman Space Telescope, designed to study dark energy and the structure of the universe, could soon provide more data about large-scale cosmic flows. Meanwhile, ongoing studies using the JWST may catch early signs of anisotropy, hints that even in the dawn of time, the universe wasn't completely balanced. If that's confirmed, it would mean the imperfection in the cosmic background isn't a glitch, it's a feature. What makes this even more compelling is that other cosmic oddities seem to echo the same theme, that the universe may be far less uniform than once believed. There are galaxies with spins that favor one direction across enormous stretches of sky. There are cosmic voids that appear larger than any simulation predicts. There are even whispers of periodic patterns in galaxy distribution, as if matter itself ripples through the cosmos in slow, ancient waves. Every new discovery seems to suggest that the universe carries memory, traces of events from before the Big Bang, or at least before the cosmos settled into its current expansion. The implications are huge. If the universe does have a built-in axis, it could mean that the Big Bang wasn't a single explosion expanding equally in all directions, but a directional event, more like a jet than a burst. It might also mean that the cosmic inflation period, the moment of rapid expansion after the Big Bang, wasn't perfectly uniform. That would change how scientists calculate the size, age, and fate of the universe. It could also open the door to entirely new physics, ideas about hidden dimensions, twisted topologies of space, or interactions between universes that stretch our understanding of reality itself. For NASA, these mysteries are not frustrating, they're exhilarating. Each anomaly is a clue, each unexpected pattern a doorway to deeper understanding. Missions that were once designed for narrow purposes, to map radiation, to detect galaxies, to measure dark energy, are now pieces of a grander puzzle. Every telescope, from Hubble to JWST, from Chandra to Planck, contributes another thread to the vast cosmic map humanity is weaving, one that grows stranger and more fascinating with every observation. Even the simplest measurements are taking on new weight. a slight deviation in cosmic temperature, a subtle shift in galactic motion, a faint polarization in ancient light. All of these can be signs of something monumental. And when NASA scientists compare notes across different missions, patterns begin to whisper from the data. Alignments that cross scales, correlations that hint at structure beyond randomness. What if the universe itself has scars? Ancient remnants of forces or collisions that once shaped it. Some physicists believe the axis of evil could be exactly that, the cosmic bruise left behind from when our universe brushed against another during inflation. Others think it's evidence of anisotropic expansion, that space itself stretches faster in one direction than another. Both ideas are radical, but neither can be ruled out. And so, NASA keeps watching. Every mission, every lens, every measurement digs deeper into the mystery. The cosmos, once thought to be simple and predictable, keeps revealing layers of complexity. The universe might not just be expanding, it might be evolving in ways we've only begun to glimpse. These cosmic oddities don't just challenge equations, they challenge imagination. They remind us that we are still at the very beginning of understanding the structure we live in. For all our technology and telescopes, the universe remains a vast, unfinished story, one where the answers are still hiding between the stars, waiting to be found. The axis of evil, the dark flow, the alignments, the unexpected brightness, these are not errors in the data, they are invitations. The universe is speaking in a language of patterns and anomalies, and NASA is learning to listen. The farther we look, the more we realize that the edge of the universe isn't a line, it's a mystery. And the deeper NASA goes, the clearer it becomes. The cosmos isn't just expanding outward, it's expanding in meaning. Black holes and the far reaches. Black holes were once only theory, dark ghosts hiding in the equations of Einstein's relativity. For decades, they lived as whispers in physics journals, described as mathematical curiosities that might exist, but probably didn't. Even Einstein himself doubted they were real. The idea that something could be so dense, so powerful, that not even light could escape its pull, sounded more like fantasy than science. But NASA would change that forever. When the first evidence began to surface, it didn't come with drama or spectacle. It came quietly, through flickers of X-rays and subtle shifts in starlight. Telescopes began catching hints that some stars were orbiting invisible companions, companions so massive that nothing could explain them except a collapsed star of impossible density. These invisible objects weren't glowing, but the matter swirling around them burned with a light brighter than anything else in the sky. Black holes, once theoretical, were suddenly undeniable. Today, NASA's telescopes peer deep into the heart of the universe, and almost everywhere they look, they find black holes, billions of them. Some are small, remnants of exploded stars. Others are monstrous, sitting in the centers of galaxies like gravitational hearts, millions or even billions of times more massive than the Sun. These are the supermassive black holes, and NASA's instruments have revealed they are far more than cosmic curiosities. They are architects of galaxies, sculptors of the cosmos. When NASA's Chandra X-ray Observatory began mapping the high-energy universe, it discovered that nearly every galaxy emits faint but distinct X-rays from its center. These X-rays are the fingerprints of supermassive black holes feeding on gas and dust. As matter spirals toward the event horizon, the invisible boundary where escape becomes impossible, it heats up to millions of degrees and glows in X-rays. What we see isn't the black hole itself, but the fury of everything it devours. In some galaxies, that fury turns into chaos. The black hole consumes so much material that it releases enormous jets of energy, blasting out matter at nearly the speed of light. NASA's Hubble and Chandra telescopes have captured these cosmic jets, stretching for thousands of light years, carving vast cavities in surrounding gas clouds. Instead of being silent destroyers, black holes become engines of creation, shaping the galaxies that orbit them. The jets they release can both trigger and suppress star formation, heating some regions while compressing others. Without them, galaxies as we know them might never have formed. What startled NASA's scientists most was how early these giants appeared. When the James Webb Space Telescope started looking deep into the past, it found supermassive black holes already fully formed just a few 100 million years after the Big Bang. That shouldn't be possible. There shouldn't have been enough time for them to grow so big. They challenge every model of how cosmic structures evolve. How could something so massive exist so early in a universe still finding its footing? Some theories suggest that the first stars, colossal, short-lived beacons known as population 3 stars, collapsed directly into black holes, skipping the usual stages. Others propose that enormous clouds of primordial gas collapsed under their own gravity before stars even formed. But even those ideas struggle to explain the scale and speed of these early monsters. The more NASA observes, the more it seems the early universe was not the quiet, gradual place we once thought. It was violent, energetic, and full of hungry giants. Infrared data from JWST adds even more intrigue. By capturing light stretched by billions of years of cosmic expansion, NASA's scientists can see through the dust that hides galactic cores. Beneath that veil, they're finding black holes that seem to grow in tandem with their host galaxies, almost like dance partners, feeding and expanding together. When one grows too powerful, it blows gas outward, starving itself for a time until the galaxy settles. This delicate balance has shaped the structure of the cosmos for billions of years. And yet, for all we know about them, black holes remain the universe's greatest paradox. They bend the laws of physics until those laws almost break. At their centers lies the singularity, a point of infinite density where time and space themselves collapse. Every theory, every equation fails there. NASA can observe the regions around black holes with astonishing precision, but what happens inside remains a mystery no telescope can touch. It's as if the universe has built its own vaults, places where its deepest secrets are locked away forever. But even from the outside, black holes defy expectations. One of NASA's most haunting discoveries came from studying what happens when they collide. When two massive black holes spiral toward each other, they twist space-time so violently that they send ripples, gravitational waves, echoing through the fabric of the universe. These waves were predicted by Einstein, but went undetected for a century. Then, in 2015, the LIGO Observatory, supported by NASA data, caught one. The signal was faint but clear. Two black holes had merged over 1 billion years ago, and the echo of their collision had just reached Earth. Since then, dozens more have been detected, and each one is like a fingerprint from the universe's most violent events. They've become a new way to see the cosmos, not through light, but through the vibrations of space-time itself. It's as if the universe finally started speaking, and NASA helped us learn how to listen. At the centers of galaxies like our own Milky Way, black holes sit quietly, mostly dormant, their immense power hidden behind a calm facade. Our own galactic heart, known as Sagittarius A*, is a supermassive black hole about 4 million times the mass of the Sun. For years, NASA's telescopes watched it flicker. Bursts of X-rays, infrared flares, subtle changes in brightness. Then, in 2022, the Event Horizon Telescope, a global collaboration supported by NASA, revealed the first image of Sagittarius A's shadow, a glowing ring of gas orbiting an invisible abyss. It was the ultimate confirmation. We weren't just theorizing about black holes anymore, we were seeing them. That image, faint and blurry as it was, marked one of the most profound moments in human history. It proved that even in total darkness, there is something to discover. And for NASA, it opened a new chapter. The agency's telescopes began to work together. Hubble, Chandra, Webb, NuSTAR, each observing different wavelengths to piece together a complete picture. X-rays showed the hot plasma. Infrared revealed the dust. Visible light traced the surrounding stars. Together they told the story of how black holes control the rhythm of galaxies. In some galaxies, these black holes are quiet giants, resting between feeding cycles. In others, they are active quasars, so luminous they outshine all the stars around them. NASA's observations of distant quasars, some existing less than 1 billion years after the Big Bang, show that these objects aren't rare exceptions. They might have been the norm in the early universe. Their light, stretched across cosmic time, still reaches us today, a whisper from an age when galaxies were young and gravity ruled like fire. Black holes also act as markers, cosmic landmarks that tell us where to look and how to measure. Their immense gravitational pull bends light, creating natural telescopes that magnify what lies behind them. NASA's use of gravitational lensing has allowed scientists to peer farther into the past than ever before, catching glimpses of galaxies that existed when the universe was less than 5% of its current age. In that sense, black holes are not just destroyers, they're gateways, bending the universe to let us see its own birth. Every year, new data brings deeper questions. Why do some black holes spin at nearly the speed of light, while others barely rotate? Why do some merge, while others remain solitary for billions of years? What happens when a black hole evaporates? Does the information it consumes disappear forever? Or does it somehow survive? These questions don't just challenge astrophysics, they challenge the nature of reality itself. NASA's role in unraveling these mysteries extends beyond observation. Through missions like the imaging X-ray Polarimetry Explorer, scientists are beginning to map the magnetic fields near black holes, trying to understand how energy escapes from something that shouldn't let anything out. These observations are rewriting what we know about particle acceleration and cosmic radiation. Even the Voyager probes, now drifting at the edge of interstellar space, continue to measure cosmic rays that may carry the faint fingerprints of distant black hole activity. What makes these discoveries so powerful isn't just their scientific importance, it's their philosophical weight. Black holes sit at the crossroads of everything we don't yet understand: gravity, time, energy, and quantum mechanics. They are the ultimate paradox, places where the universe writes its most mysterious equations in invisible ink. When NASA looks at them, it's not just studying objects, it's studying the limits of existence. Every image, every spectrum, every flicker of light carries meaning. When Chandra detects an X-ray burst from a galaxy 10 billion light-years away, that's light born before our planet even existed. When JWST catches the faint glow of a dusty quasar, it's seeing a memory of the universe building itself. Each observation is a time machine, each discovery a piece of a cosmic autobiography billions of years long. And in that story, black holes are the punctuation marks, the silent pauses that hold meaning in between the explosions of creation. They remind us that even in destruction there is design, that even in silence the universe speaks. NASA's scientists often say that the more they learn about black holes, the more mysterious they become. They break every rule, bend every boundary, and refuse to fit into the neat boxes of theory. They're both the simplest and most complex objects we know: pure gravity, pure energy, pure enigma. But perhaps that's what makes them so captivating. They're proof that the universe doesn't just exist, it creates, it builds, it destroys, it reinvents. And through NASA's eyes, we get to watch it happen. Beyond the comfort of familiar stars, black holes pull galaxies into being, anchor clusters, and shape the very fabric of space-time. They are not just the edge of physics, they are the edge, the point where knowledge meets mystery. Each discovery feels less like an end and more like a beginning. Because wherever a black hole waits, there's something beyond it, something unseen, something that might rewrite everything we think we know about the universe. The expanding universe and the fate of everything. The universe is not static. It never was. Every galaxy, every star, every particle of dust is moving, not through space, but with it. Space itself is stretching. This was one of the most shocking discoveries in human history, and it came not from philosophy or speculation, but from observation. When Edwin Hubble looked through the Hooker telescope at Mount Wilson in the 1920s, he found that galaxies were drifting away from us. Their light was stretched toward the red end of the spectrum, a sign of recession. The farther a galaxy was, the faster it fled. It was a universal expansion, a grand unraveling that began from a single incomprehensible point. That revelation changed everything. The static cosmos of Newton became the dynamic, evolving universe of modern cosmology. NASA inherited this legacy and turned it into a pursuit that spans decades. Its missions have not only confirmed the expansion, but measured its rhythm, shape, and possible destiny. Through instruments like the Hubble Space Telescope, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck mission, scientists have traced the universe's history with extraordinary precision. Every flicker of light holds a record of cosmic motion, a map of time itself, written in photons. The story these missions tell is both magnificent and unsettling. The universe is not just expanding, it is accelerating. In the late 90s, two independent teams studying distant supernovae discovered something no one expected. Galaxies weren't slowing down as gravity should dictate. They were speeding up. Something invisible was driving them apart faster and faster. That something was called dark energy, a term that hides more mystery than meaning. Dark energy makes up roughly 70% of the universe. No one knows what it is. It has no scent, no color, no texture. It doesn't clump like matter or emit light like stars. It seems to exist only as a property of space itself, a pressure that resists gravity. NASA's data from Hubble and WMAP confirmed its dominance, showing that the universe's geometry is almost perfectly flat, balanced between expansion and collapse. Yet this balance is fragile, and the repulsive push of dark energy is winning. The galaxies visible today will one day fade from sight. As expansion accelerates, light from distant systems will stretch beyond the reach of any telescope. Future observers, if any exist, may look into the sky and see only the faint glow of a single galaxy, unaware that billions once filled the void. The night will not always look like this. Hubble's deep-field images, capturing galaxies billions of light-years away, are time capsules of an era that will eventually vanish from visibility. Every spiral and elliptical form we see in those pictures is a ghost from the past, a memory carried by light that traveled across cosmic time. The acceleration ensures that such light will one day never arrive. What we observe now is a privileged moment, a brief interval when the universe still speaks to us in full chorus. NASA's newer instruments extend that story. The James Webb Space Telescope looks deeper into infrared wavelengths, revealing the earliest galaxies, fragile, chaotic clouds of stars, forming less than 500 million years after the Big Bang. Its data show that structure appeared faster than anyone predicted. Galaxies were not supposed to be so mature so soon. The expansion did not dilute creation, it amplified it. Matter gathered, stars ignited, black holes formed, and entire clusters took shape amid the expanding fabric of space. Yet, this dynamic growth hides a countdown. The more the universe stretches, the colder and darker it becomes. The average temperature of the cosmic background radiation, the faint afterglow of the Big Bang, has fallen from thousands of degrees to just a few degrees above absolute zero. It continues to drop as space dilates. The light from the first stars still travels, but each wave is stretched thinner, dimmer, fainter. Entropy is winning its quiet war. The fate of everything may depend on the true nature of dark energy. If it remains constant, as Einstein's cosmological constant suggests, the universe will expand forever. Galaxies will drift apart until their light can no longer reach each other. Stars will burn out, leaving only remnants: white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even those will decay, leaving a cosmos of cold particles and fading radiation. This scenario, often called the heat death, is a universe that ends not with a bang, but with eternal silence. There are other possibilities. If dark energy grows stronger, expansion could accelerate to the point where it tears galaxies, stars, planets, and even atoms apart. A cosmic disintegration known as the Big Rip. If, on the other hand, dark energy weakens or reverses, gravity might one day halt expansion, pulling everything back together in a big crunch. Some physicists imagine that such a collapse could trigger a new Big Bang, giving birth to a fresh universe, a cycle without beginning or end. NASA's future missions aim to narrow these possibilities. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, is designed to measure cosmic expansion with unprecedented accuracy. By mapping billions of galaxies and observing thousands of supernovae, it will trace how dark energy has changed over time. Its results could confirm or completely overturn current models. Even a small variation in the behavior of dark energy would rewrite the timeline of existence. Behind every number lies a deeper question. Why does the universe exist in a state that allows life to perceive it at all? The rate of expansion is balanced so delicately that even a tiny difference would have erased the possibility of stars, planets, and observers. If gravity were stronger, the universe would have collapsed long ago. If expansion were faster, matter would never have condensed into galaxies. The fine-tuning is so precise it defies easy explanation. Some scientists turn to the idea of the multiverse, countless universes with different laws, most barren, some briefly fertile. Others suggest that what we call fine-tuning is a reflection of selection. We observe this universe because only such a universe allows observation. Still, the numbers carry awe. The observable universe spans at least 93 billion light-years, yet this is only the part we can see. Beyond that horizon, space continues, perhaps infinitely. NASA's maps of the cosmic microwave background show uniformity across vast distances, suggesting that all regions once touched, then drifted beyond each other's reach. The fabric stretches, and with every second, more of it slips away from any possible communication. Even light, the fastest traveler, cannot bridge the widening gulf. There is something almost tragic in that. The galaxies we see through Hubble or Webb are not merely far, they are unreachable forever. Their light is the last message they will ever send. The cosmos is separating not through hostility, but through inevitability. Expansion is not a choice, it is destiny written into the equations of spacetime. Yet within this expanding arena, creation continues. New stars ignite in the arms of galaxies. Supernovae scatter heavy elements that seed future worlds. Black holes merge, sending ripples through spacetime. Even as the universe stretches, it builds complexity. Gravity resists dispersion by weaving matter into structures, clusters, filaments, superclusters. NASA's observations of the cosmic web show a vast architecture of matter connecting everything, a three-dimensional lattice of light and gravity that resembles neural networks in form, if not in scale. This structure may hold clues to the universe's ultimate balance. The filaments of galaxies and the voids between them reveal how dark matter shaped cosmic evolution. Dark matter, like dark energy, cannot be seen directly, but its presence is undeniable. It makes up about 27% of the universe and provides the gravitational scaffolding on which galaxies form. Without it, the visible matter would never have gathered. NASA's lensing studies, using the way gravity bends light, have traced the invisible contours of this hidden substance, painting an outline of the unseen. The expansion continues, but not evenly. Some regions expand faster, some slower, depending on the distribution of mass and energy. The cosmic web is not a smooth balloon, but a textured, restless field. NASA's data from the Cosmic Background Explorer, WMAP, and Planck show faint fluctuations, ripples left over from the earliest moments of creation. These ripples became the seeds of galaxies. Each pixel of the cosmic microwave background map is a record of ancient sound waves frozen in light. From those tiny variations, everything familiar was born. Every discovery folds into the next. Expansion reveals dark energy. Dark energy forces questions about quantum fields. Quantum theory suggests that empty space should contain vast energy, yet the observed value is incomprehensibly smaller. The mismatch between theory and measurement is the largest discrepancy in physics, a reminder that our equations, however elegant, still miss something essential. NASA's mission is not to answer everything, but to measure carefully enough that truth reveals itself. Its telescopes operate at the threshold of perception, catching photons that have traveled for billions of years. Each observation is an act of translation, turning faint, ancient signals into meaning. What emerges is not a static picture, but a living story of expansion, transformation, and inevitable decay. If expansion defines the universe's motion, then time defines its direction. Every second that passes increases entropy, spreads energy thinner, and moves everything closer to equilibrium. Yet, within that descent toward disorder, islands of order form. Stars, planets, and life itself are temporary defiance. Local pockets where energy flows create structure instead of chaos. NASA's search for exoplanets and biosignatures is a search for other defiant places, other sparks of complexity in the vast, cooling night. The future may belong to darkness, but the present is filled with light. For now, expansion gifts us a sky still alive with history, galaxies blooming in silence, quasars blazing at the edge of visibility, nebulae unfurling in slow motion. Each image Hubble or Webb sends back is a reminder that we live during the universe's luminous era, when creation is still visible. Far ahead, perhaps trillions of years from now, that will no longer be true. The stars will fade, the galaxies will dissolve, and the cosmic web will unravel into isolation. Space will stretch until even black holes evaporate through Hawking radiation. What remains will be a thin haze of particles drifting in an ever-expanding void. There will be no witnesses then, no instruments to record the silence. Yet, this long future is not melancholy. It is part of a larger rhythm that may exceed comprehension. If the universe can emerge from nothing once, perhaps it can again. The energy of vacuum, the fluctuations of quantum fields, and the laws of physics themselves may ensure that existence never truly ceases. The universe may not have a final act, only endless variations of beginning. NASA's telescopes cannot see that far ahead, but they have given us the tools to understand that such questions are worth asking. Each discovery, from the first redshift measurement to the mapping of the cosmic microwave background, has drawn a clearer outline of a living, breathing cosmos. It is not a closed system, but an evolving one, a process rather than a product. The expansion continues. Every observation confirms that space stretches faster than our capacity to grasp it. And yet, within that expansion, meaning persists. The act of measurement, the effort to understand, becomes a form of resistance against dissolution. As long as there are eyes to see and instruments to build, the universe has not ended. The fate of everything is not just an astrophysical question, it is a human one. To study the expansion is to face impermanence. Everything we know, every planet and star, exists in the brief window between creation and dissolution. But within that window lies consciousness, the capacity to recognize the universe, to name its forces, to chart its growth. That awareness may be fleeting, but it is also the universe's way of seeing itself before the lights dim. Expansion is not destruction, it is evolution. It is the cosmos breathing outward, carrying with it the legacy of every photon ever emitted. NASA's mission, at its deepest level, is to follow that breath, to map it, understand it, and share the story before it fades. The data becomes memory, the memory becomes meaning, and meaning becomes our way of existing within the infinite. The universe expands. It will keep expanding. But for now, it remains visible, a masterpiece in motion, written in the light of 1,000 billion suns, all receding but never forgotten. Space is not empty. It only looks that way. Beneath the black canvas of the universe lies a fabric, something fluid, elastic and alive with invisible motion. It bends, it ripples, it stretches. It carries light, gravity and time itself. This is space-time, the silent stage where all matter performs its dance. And though we live within it, we have only begun to understand its hidden architecture. The hidden architecture of space-time. For centuries, space was thought of as nothing, an endless void, a backdrop without form. Then came Einstein, who showed that space and time are woven together, inseparable and dynamic. Mass bends this fabric, and that curvature tells planets and stars how to move. Every orbit, every falling apple, every collapsing star is the result of geometry, not invisible forces pulling through emptiness. NASA's work has turned this theory into tangible evidence. Its telescopes don't just observe stars and galaxies, they see the shape of space-time itself through the way it bends light. When the light from a distant galaxy passes near a massive cluster of galaxies, gravity acts as a lens, warping and magnifying that light. It's called gravitational lensing, and it allows astronomers to look farther than any single telescope could. In Hubble's images, these distortions appear as arcs and smears of light, ghostly rings surrounding massive objects. But to NASA scientists, they are maps of the invisible. Each curve marks a place where gravity has reshaped space. Each lensing effect draws a contour of the cosmic web's underlying structure. The universe, it turns out, is not arranged randomly. It's patterned by the interplay of dark matter and energy, woven through geometry. This bending of light has revealed some of the universe's most profound secrets. It has shown hidden galaxies buried behind others, magnified distant quasars that would otherwise be invisible, and even allowed astronomers to weigh galaxy clusters by their gravitational effect alone. Through this lens, space itself becomes a tool for observation. The universe is looking at itself through its own distortions. But lensing is only one layer of the story. Beneath the grand architecture of galaxies and filaments, there may be smaller, stranger patterns, structures that twist space-time in ways we can barely imagine. Theoretical physics speaks of wormholes, tunnels that connect distant regions of space and time. They're not proven, but they're mathematically possible. If space-time can bend, in theory, it can also fold. NASA has never observed a wormhole directly. No one has. But its data provides the boundaries within which such exotic phenomena might exist. The gravitational waves detected by LIGO and later confirmed by NASA missions have shown that space-time does ripple, that it can carry vibrations like a vast cosmic ocean. These ripples are born from cataclysms, the collision of black holes, the merging of neutron stars, events so violent they shake the fabric of reality. When two black holes spiral into each other, they warp space-time so intensely that it rings. NASA's involvement with these detections, through its collaborations with the European Space Agency and projects like LISA, Laser Interferometer Space Antenna, is paving the way for space-based observatories that will capture these waves from millions of miles away. Each signal is like a note in the universe's deep, slow symphony. A story of matter becoming energy, energy becoming motion, motion becoming geometry. The discovery of gravitational waves didn't just confirm Einstein's theory, it opened an entirely new way of seeing. For the first time, we can listen to the universe instead of just looking at it. Light can be blocked or absorbed, but gravity's waves travel freely through everything, through stars, dust, even entire galaxies. They carry information about the unseen, the unseeable, the moment two singularities collide, the shape of space-time around them, the echo of creation itself. Some of the strangest ideas in physics emerge when we try to unite this geometric universe with the quantum one. At the smallest scales, the smooth fabric of space-time breaks down into a restless foam. Space flickers. Time fluctuates. Virtual particles pop in and out of existence. What looks continuous on the cosmic scale becomes turbulent at the microscopic one. NASA's missions are not designed to probe the quantum directly, but they provide the clues. Every observation of cosmic microwave background radiation, every measurement of the universe's geometry adds a piece to the puzzle. The early universe, when it was less than a second old, was a place where quantum mechanics and relativity coexisted, a realm of infinite density and unimaginable heat. To understand the present, scientists must reach backward through observation and forward through theory, stitching them together across billions of years. At the heart of this search lies the idea that space-time itself might be emergent, that it arises from something deeper, something not made of matter or energy, but of information. Some physicists suggest that the universe is built like a hologram. Every point in space encodes the information of a larger whole. NASA's observations of black holes have lent weight to this possibility. When a black hole forms, it hides information behind its event horizon, the boundary beyond which nothing can escape. Yet according to quantum theory, information can't be destroyed. So where does it go? Decades of research, sparked by Stephen Hawking's work and supported by NASA's data, suggest that the information might be preserved in the surface area of the horizon itself. Space is not a void, but a storage device. The cosmos may be a vast self-encrypting memory. If that's true, then gravity, time, and the structure of reality could all emerge from how information is arranged and exchanged. NASA's role here is not to solve the equations, but to provide the evidence that drives them. The precision measurements, the anomalies, the boundaries that theory must respect. Every unexpected signal from a distant quasar or faint ripple in background radiation is a potential crack in our current understanding. Some researchers propose that the universe might contain cosmic strings, infinitesimal, one-dimensional defects left over from the Big Bang, stretched across the cosmos like tension lines in space-time. They would be thinner than an atom, but longer than galaxies, carrying enormous energy. None have been found yet, but NASA's instruments are sensitive enough to detect their fingerprints if they exist. Gravitational lensing distortions, ripples in the cosmic microwave background, or bursts of radiation from string collisions. These possibilities sound like science fiction, but every major breakthrough once did. When Einstein first described curved spacetime, it was dismissed as abstract speculation. When Hubble proved the expansion of the universe, it was unthinkable. When the first exoplanet was found, it rewrote our definition of normal. NASA's ongoing work continues that lineage, turning the incredible into the inevitable through patience, precision, and vision. The James Webb Space Telescope, though famous for its beautiful images, is also a machine for mapping spacetime. Its infrared sensors penetrate dust clouds that hide the centers of galaxies, revealing black holes and the stars orbiting near them. By tracking these orbits, NASA scientists can measure how gravity behaves under extreme conditions, where relativity is tested at its limits. Webb's observations have already shown galaxies forming around central black holes far earlier than expected, suggesting that spacetime organizes itself more rapidly than our models predict. Then there is Chandra, NASA's X-ray observatory, which sees the high-energy universe invisible to our eyes. It detects the radiation from hot gas swirling near black holes, from the remnants of supernovae, and from galaxy clusters where dark matter anchors visible matter in place. These observations reveal how energy flows through spacetime, how matter collapses, heats, and transforms into radiation. Each X-ray photon tells a story of motion through curved geometry, a moment of interaction between gravity and energy. The cosmic web, the vast network of filaments and voids stretching across the universe, is another manifestation of spacetime's architecture. NASA's maps show how galaxies cluster along these filaments, connected by the invisible gravity of dark matter. The pattern looks almost biological, like neurons linked in a brain. This structure may reflect the underlying mathematics of spacetime itself. Order emerging from expansion, connection arising from emptiness. But even this grand architecture may be temporary. As the universe expands, distances grow, and gravitational bonds weaken. The web will stretch thinner, its filaments fraying into isolation. Over billions of years, the fabric itself will flatten, the curvature that once sculpted galaxies smoothing into uniformity. If dark energy continues to dominate, spacetime will become increasingly featureless, a vast cold geometry devoid of form. NASA's missions are snapshots of this transition. They capture the universe not as a static object, but as a moving structure, mid-motion, mid-transformation. The data from Hubble, Chandra, and Webb are chapters in a story that began before atoms existed and will continue long after stars die. Together, they reveal that space is not a void to be crossed, but a medium that defines everything. This realization changes how we think about existence itself. If space and time can bend, ripple, and perhaps even emerge from deeper laws, then the universe is not a stage for reality. It is reality. Everything that has ever happened, from the birth of galaxies to the thoughts passing through a human mind, unfolds within the same malleable fabric. To explore space, then, is to study the architecture of being. And that's what makes NASA's work so profound. It's not just about telescopes or data. It's about building a bridge between the visible and the invisible. The discoveries written in numbers and light curves are glimpses into the scaffolding of existence, into the way everything holds together. Each mission reaches a little deeper into that hidden architecture, revealing that space is more than distance and time is more than duration. They are the pulse of the cosmos, the structure of reality itself. The farther NASA looks, the clearer the pattern becomes. Matter tells space-time how to curve, and space-time tells matter how to move. From that relationship arises everything: stars, galaxies, gravity, and even us. We are built into the fabric we study. To understand it is to see ourselves not as observers standing outside the universe, but as part of its living geometry. The hidden architecture of space-time is not beyond reach. It's here, underfoot and overhead, present in every orbit and every photon. NASA's telescopes don't just explore distant galaxies. They show us the shape of the space we already inhabit. The same curvature that bends light around a galaxy also bends the paths of the planets and the fall of rain on Earth. The same equations that describe black holes describe the ticking of your clock. Space is not elsewhere. It's everything. Humanity at the cosmic edge. For most of human history, the sky was a mystery painted in light. People looked up and saw patterns, gods, animals, omens, but never imagined they were staring into infinity. The universe was a ceiling, not an ocean. Then NASA and generations of scientists began to push beyond that ceiling, and what they found changed everything we thought we knew about existence. Every discovery made at the edge of the observable universe, from galaxies forming just after the Big Bang to the mysterious energy-accelerating cosmic expansion, has done more than expand our scientific understanding. It has expanded us. The deeper NASA looks into the cosmos, the deeper humanity begins to look inward, asking the questions that science alone can't answer. Why are we here? What does it mean to exist in a universe so vast that our entire world is smaller than a grain of dust in comparison? These discoveries matter not just because they rewrite textbooks, but because they rewrite our place in reality. When NASA revealed that the universe is not static but expanding, it shattered the illusion of permanence. Everything, from the stars above to the atoms in our bodies, is part of a dynamic, evolving story. When the Hubble telescope captured galaxies billions of light years away, it didn't just show us the past. It showed us that we are part of something unimaginably larger and yet intimately connected. That realization changes how people think, dream, and even live. The moment humans grasped that the light reaching their eyes could have begun its journey before Earth existed, something shifted in our collective perspective. Suddenly, human life, with all its chaos and beauty, became part of a cosmic narrative billions of years in the making. We were no longer just inhabitants of a planet. We were participants in the evolution of the universe itself. The psychological effect of this is profound. For some, it's humbling. It forces an awareness of how small we are, how temporary, how fragile. The universe will continue long after humanity's last footprint fades from the Earth. Our lives, our empires, our achievements, they vanish in cosmic time like sparks in a storm. Yet for others, that very smallness is liberating. If we are such a fleeting moment in an endless cosmos, then every moment we do have becomes infinitely precious. NASA's work at the cosmic edge gives meaning to both awe and humility. Each image from the James Webb Space Telescope or Hubble is more than data. It's a mirror. When we stare at those glowing arcs of ancient galaxies, we're not just looking at the universe, we're looking at ourselves, at the material that built us, at the story written in our atoms. The iron in our blood, the calcium in our bones, the oxygen in our lungs, All were forged in the hearts of stars. When those stars died, they seeded the cosmos with the elements of life. That is not a metaphor. It's literal truth. We are made of stardust. This connection turns the distant universe into something personal. The light we observe at the edge of the cosmos is the same light that eventually became us. When NASA maps cosmic radiation or captures the birth of a galaxy, it's not just studying space, it's uncovering the origins of everything human. That realization has a way of blurring the lines between science and philosophy. The great paradox of NASA's discoveries is that the more the universe expands in our understanding, the more we realize how connected everything is. The cosmic web, those vast filaments of galaxies and dark matter stretching across billions of light years, is not just a structure of space, but a metaphor for reality itself. Every star, every world, every living thing is woven into a single tapestry of existence, bound by the same physical laws and the same origin. This knowledge changes how we see life. It pushes us to look beyond national borders, beyond species, beyond the limits of the moment. If everything in the universe came from the same beginning, then separation is an illusion. We are part of the same event, the same breath of creation still unfolding. NASA's pursuit of the cosmic edge has also transformed how humans create and imagine. Science fiction, once the domain of dreamers and futurists, suddenly became more grounded in truth. Concepts like wormholes, multiverses, and time dilation, once fantasy, now echo real possibilities suggested by physics. Films, novels, and art are inspired by data, by images of galaxies so distant that their light began traveling before our planet formed. The line between science and imagination grows thinner with every mission. When the first images from Hubble arrived, they didn't just thrill astronomers, they inspired artists, writers, and ordinary people. Paintings, music, films, and entire genres of storytelling began to reflect this new vision of the universe, one where humans are explorers, not of continents, but of creation itself. NASA gave humanity something more powerful than knowledge. It gave us perspective. And that perspective has psychological consequences. It's difficult to feel hatred or pettiness when you see yourself as a part of something infinite. The famous pale blue dot image, captured by Voyager 1 at NASA's direction, showed Earth as a tiny speck suspended in a sunbeam, less than a pixel in the vastness of space. Carl Sagan's reflection on that image still resonates. Every king and pauper, every saint and sinner, every love story, every war, all of it happened on that dot. That perspective is both terrifying and profoundly beautiful. The discoveries at the edge of the universe remind humanity that our survival is not guaranteed, that we are temporary passengers in an ancient cosmos, but they also reveal that the very act of looking is miraculous. Out of countless galaxies, on one small planet orbiting an average star, life arose, and that life learned to look back at the universe that made it. That might be the most extraordinary fact of all. NASA's work also touches something deeply emotional: the human need to belong. In a universe so large it defies comprehension, it's easy to feel lost. Yet every discovery suggests the opposite. We are not lost. We are exactly where we should be. The universe is not indifferent. It created the conditions for consciousness to exist, for curiosity to bloom, for questions to be asked. In that sense, we are the universe's way of understanding itself. Every photograph of a galaxy, every measurement of a cosmic wave, every signal captured from billions of light years away, they are moments of the universe recognizing its own reflection. When NASA scientists study the cosmos, they are participating in a dialogue as old as existence itself. The impact of this understanding reaches far beyond science. It reshapes religion, philosophy, art, and even politics. It demands a new kind of humility and a new kind of responsibility. If the cosmos is one, and everything in it shares a common origin, then how we treat our planet and each other matters on a cosmic scale. Our choices ripple outward, part of a universal continuum that began with the first spark of creation. Popular culture mirrors this awakening. Modern stories, from Interstellar to The Expanse, blend scientific reality with existential reflection. They echo NASA's message. Space is not just a setting, it's a question. It asks who we are, why we exist, and what it means to keep searching even when answers feel unreachable. The universe is not cold, it's alive with meaning. And our exploration of it is not just about discovery, it's about identity. NASA's discoveries remind us that we are not standing outside the universe looking in. We are the universe, in human form, looking at itself through time. The edge we seek out there is the same boundary we encounter within, the limits of understanding, the threshold of wonder. At the cosmic edge, humanity finds both insignificance and belonging, fear and purpose. We may never know what lies beyond the observable universe, but what matters is that we continue to look. Because the act of searching, of reaching beyond our grasp, is what makes us human. And perhaps that is the real discovery. That in exploring the vastness of space, we discover not just stars or galaxies or cosmic mysteries, but the infinite capacity of the human spirit. To wonder, to learn, and to never stop asking what lies beyond. The universe looking back at us. When NASA points its telescopes toward the distant reaches of the cosmos, it's easy to think of the act as one-directional, humanity gazing outward, trying to uncover the secrets of existence. But the deeper the discoveries go, the clearer it becomes that something else is happening. The universe, in its own silent way, is looking back. Every time a new image returns from Hubble or the James Webb Space Telescope, it feels less like data and more like a revelation, a reflection. The colors, the patterns, the ancient light captured in those images aren't foreign. They're familiar because they are echoes of the same forces that shaped us. Every atom, every photon, every particle in our bodies shares its origin with the light we see at the edge of time. That means that every observation, every discovery, is also an act of self-recognition. When NASA scientists study the oldest galaxies or map the faint whispers of the cosmic microwave background, they're not just studying the universe, they're studying what they are made of. Humanity is, quite literally, the universe becoming aware of itself. It's easy to forget this when surrounded by the noise of everyday life, traffic, deadlines, endless digital distractions. But step outside on a clear night, and the connection returns instantly. The light from those distant stars has traveled for billions of years through space, across impossible distances, just to meet your eyes. You are, for that brief moment, part of a conversation that began at the dawn of time. NASA's work at the cosmic frontier has turned that poetic truth into measurable reality. The photons detected by the James Webb Space Telescope are not just old, they are ancient, dating back to when the universe was less than 1 billion years old. That light began its journey long before the Earth formed, long before life emerged, long before there were eyes capable of seeing it. Yet here it is, captured by instruments built by human hands. Proof that existence has come full circle. The universe doesn't communicate in words or sound. Its language is light, and that light carries stories older than imagination. Every observation becomes a kind of mirror, showing us not only what is out there, but what has always been inside us. The realization that we are part of the same story we're studying changes the meaning of discovery itself. Science is no longer about separation, the observer and the observed, but about reunion. The more NASA learns, the more it becomes clear that the boundaries we draw between human and cosmic, between the personal and the infinite, are illusions. When Hubble captured the ultra-deep field, a single image filled with thousands of galaxies, each containing billions of stars, astronomers described it as looking into eternity. Yet the deeper truth was even more extraordinary, that eternity was looking back. Within those galaxies are the same laws of physics, the same chemistry, the same elements that exist here on Earth. The same processes that formed those distant worlds shape this one too. We are made of the same materials as the stars that shine in that ancient light. NASA's discoveries show us that the universe is not indifferent. It is creative. It builds complexity, nurtures matter into stars, stars into worlds, and worlds into life capable of asking questions. The edge of the universe isn't just a limit of observation, it's the edge of comprehension, the frontier where curiosity meets creation. And perhaps this is why the universe feels so deeply human when we study it. It reflects our own patterns, cycles of birth and death, of destruction and renewal. Galaxies collide, merge, and evolve. Stars explode, scattering the elements of future generations. Even black holes, those cosmic enigmas of gravity, are not just destroyers but sculptors, shaping the galaxies around them. The universe is not chaos, it's order in motion, a living pattern always unfolding. Through NASA's eyes, we see that pattern at scales that defy comprehension. But it also mirrors something intimate: the structure of neurons, the branching of trees, the flow of rivers. Nature repeats itself across size and distance, as if reminding us that the cosmos is both vast and deeply connected. We are not small fragments lost in it, we are expressions of it. That realization has an emotional gravity of its own. It turns awe into belonging. When the James Webb Space Telescope captured its first deep-field image, a glittering sea of galaxies shining through the dark, it was hailed as humanity's farthest look into space. But in another sense, it was humanity's deepest look into itself. Those galaxies are not just out there, they are part of the same universe that lives within us. There is something profound in knowing that the light we study has been traveling for billions of years, only to end its journey in the lens of a telescope built by a species that just recently learned to walk upright. The odds of this, of consciousness arising from stardust, of curiosity surviving long enough to build machines that see beyond time, are beyond comprehension. And yet, here we are, tracing the universe's own reflection back to its source. The more NASA observes, the more it becomes clear that the universe is not just a place, it's a process. It's not something we stand outside of, it's something we are inside of, part of, and made from. The boundaries between observer and observed vanish when we realize that the atoms forming our eyes were once part of the stars we're looking at. In this way, every NASA mission becomes an act of self-awareness on a cosmic scale. The telescopes, satellites, and probes are extensions of human curiosity, mechanical eyes reaching beyond the cradle of our solar system. But the desire behind them is ancient, primal. The same spark that once led our ancestors to map the stars on cave walls now drives us to map the universe itself. This is why the discoveries at the cosmic edge resonate so deeply. They don't just tell us about the universe, they tell us about us. They remind humanity that we are not separate from the cosmos we study. We are its latest expression, its most self-aware creation. When NASA scientists describe their work, there's often a quiet awe in their tone, not just because of what they find, but because of what it means. The more they learn, the more they realize that the universe is not just expanding in space, but in understanding. Every new discovery stretches the boundaries of human consciousness, making room for wonder that didn't exist before. Perhaps that's what the edge of the universe truly is. Not a physical boundary, but a mental one. The point where knowledge meets mystery, where light meets darkness, and where curiosity becomes creation. The universe looking back at us is not a metaphor, it's the truth of existence itself. The cosmos has found a way to see itself, through human eyes, through NASA's lenses, through the act of asking questions. The universe isn't silent, it speaks through us. And when we look up, we're not staring into emptiness. We're staring into a reflection so vast, so old, and so full of meaning that it humbles and empowers us all at once. The edge of the universe isn't far away. It's right here, in the connection between what exists out there and the consciousness that dares to look.